Kia ora koutou, I'm Greg O'Byrne. Welcome to today's lecture, which is entitled Principles of Sound Applied to Hearing Assessment and Management. This forms part of Here 243, Intro to Audiological Assessment and Management. So as future speech and language therapists, and dare I say it, future audiologists, you're going to want to know a lot about sound. It's a key part of the role that you're about to undertake. And so what I'm going to talk to you today about is a whole range of topics relating to sound, how we describe it, its effects on the ear, how it behaves in environments such as the one that I'm in right now, and other more sort of echoic environments, ones that are sort of maybe hard-walled and where sound bounces around a lot more. So you'll learn all about those sorts of things and how you can apply those thoughts and those techniques to the spaces in which you operate as part of your role, but just in everyday life. So we're going to be covering a lot of topics. By the end of this session, you should understand sound waves, what sound is, and how we describe the properties of a sound. What things do we need to talk about in order to fully describe, for example, a sine wave? And these are terms such as amplitude, frequency, and phase. You'll also learn that the human ear doesn't respond the same to different frequencies. It's more sensitive to some frequencies, and other frequencies the ear is less sensitive to, and so we need to put more energy in order for it to sound the same level as some other frequencies. We'll talk about the decibel scale. You've probably all heard the term decibels, but you're aware that like a large number of decibels means it's louder. But what does that mean exactly? How do we use decibels when we're describing sound? There are different types of decibels, different flavors, different scales, and what determines which decibel scale we use at any given time. You'll learn what sound level meters do, and also, so sound level meters basically just give you the overall level of the sound without any reference to what frequency that sound is at. But we can also do spectral analysis, which is a tool that enables us to actually look at the levels of all the sounds at all of the frequencies, and that's extremely useful. We'll talk about an audiogram and how that relates to the sounds that we hear. So you're probably all familiar with the audiogram from last week's lecture, but we're going to go into that in a little bit more depth. We'll talk about the difference between pure tones and more complex sounds. What are the ingredients of those things? And we'll talk about the idea of calibration, what it is and why we do it, why we pay attention to it, and why is it important. We'll also learn how sound propagates around objects and into and within rooms. This is really important when it comes to providing good, for example, learning environments. In schools, we need sound to not make its way into classrooms from busy roads that are nearby, but also, obviously, kids are noisy. They're going to generate a lot of sound. How do we stop that sound bouncing around and hanging around for too long and making the environment more noisy overall? There are various techniques that we can use to deaden down that sound. And some of that feeds into the concepts of reverberation and reverberation time, and I'll explain and give examples of each of those things. And examples of how the acoustics of classrooms can be improved, but not just classrooms, also audiological testing environments and the therapy rooms that you might use for speech and language therapy. Okay, so firstly, what is sound? You may not be aware of it right now, but we are currently standing on the surface of the Earth underneath a column of air which is several hundred kilometers high. It extends all the way up to the top of the atmosphere. And that air has mass and it has weight and it pushes down on us, and that we feel that as pressure. We call that atmospheric pressure. So it's exerting force on everything around us. It's pushing in on us from all angles. Air has a certain mass, but you probably are aware that when you, say, swim underwater, because water is so much more massive, there's a lot more pressure. You might feel that on your ears as you're trying to dive down, for example. So that's just the concept of pressure. We are surrounded by it all the time. So if I walked outside right now, I would be, and indeed in here, because the window's open, I am subject to normal atmospheric pressure. It's relatively static or unchanging. So it's around 101.3 kilopascals, as I'll describe in a moment. But with weather systems, for example, you might remember on a weather chart, you see there's high pressure systems moving around and low pressures. And so there's a low coming up or there's a high coming up. What that's talking about are subtle variations in atmospheric pressure. So that is atmospheric pressure, but it is not sound. Sound is very, very tiny fluctuations in that pressure. I'm producing those fluctuations right now by talking. So by forcing air through my vocal cords, I'm causing them to vibrate. And that is increasing and decreasing, cycle by cycle, the air pressure around me. So, and that's audible. It's picked up by these microphones here. So that is what sound is. It's tiny, rapid variations around that standard atmospheric pressure. So imagine we've got here's a scale going from this desk up to here. This is atmospheric pressure. And then the sound that I'm producing is a wobble on top of that standard atmospheric pressure. So here's the average. If it's dead silent, we're right here. If the pressure increases, it goes above that average. If it decreases, it goes below that average. And it's doing that thousands of times a second, depending on the frequency that I'm producing. So something like is about 100 hertz. So it will be going up and down 100 times a second. Something like is more like 1,000 hertz. And so that would be going up and down 1,000 times a second. Now on this scale, this isn't the size of that variation. This is ridiculously large in comparison to the actual size of sound, which is very, very tiny. Humans can detect sound from a different range, a really wide range of frequencies. So the lowest frequency that we can hear is 20 cycles per second. So that means the sound pressure is going up and down 20 times per second, all the way up to 20 kilohertz, 20,000 hertz. And that means it's going up and down 20,000 times a second. When I say humans, I mean most likely you rather than me. The younger you are, the better your high frequency hearing is, and it tends to decrease with age. That higher limit tends to decrease with age, unfortunately. And it's not helped by things like exposure to loud music, for example. That's something which will decrease your ability to hear certain frequencies. Certain pharmaceuticals and drugs will also affect your hearing. All right, so as I said, these sound pressure waves are incredibly tiny, and we call these sound waves. Do they have to be in air in order to be sound? So I've spoken about sound fluctuations as moving through air, but do they also move through other media, other fluids? So air is a fluid, for example. What's another fluid? Water, for example. Does sound move through water? Can you hear anything if you're underwater? The answer is yes. Sound moves very well through water, and it can travel very long distances underwater. The reason things sound quiet when you get underwater compared to the outside, you might have difficulty hearing someone who is standing above a pool if you're underwater. And that's because of the junction between the air and the water. The sound has difficulty passing through it and bounces off. But sound can travel very easily through water. And in fact, it travels a lot quicker in water. We'll talk about that a bit more in a moment. Can sound travel through solid objects? Is that a thing that's possible? Well, if you've ever been inside a sealed room and heard someone like the neighbors next door, that's an example of sound traveling through the walls. It's through a solid object. So sound can travel through air, it can travel through liquids, it can travel through solids. Basically anything that is capable of vibration will be able to transmit sound. The only thing sound can't travel through is a vacuum, because there's an total absence of anything. So it can't travel through a vacuum because there's nothing to vibrate. There's no pressure, and therefore nothing to have a pressure fluctuation. It's that line in space, no one can hear you scream. Okay, so what are waves and how do we describe them? When an object vibrates, any object, when it vibrates, that oscillation causes a periodic disturbance in the medium that surrounds it. So that might be air, might be fluid, or it might be the solid that it's attached to. And that vibration radiates out in straight lines in the form of a pressure wave. So if we take, for example, have you all heard of a tuning fork? Here's some examples of tuning forks. There's a lovely array of them right here. These all have different sizes and shapes. and some of them vibrate at different frequencies to others. So if I take this here and give it a twang, you might not be able to hear that, but I'll place it close to my microphone. So that there is producing a frequency, it says here, of 256 hertz. All right, so if I hit this tuning fork on my knee, for example, the prongs at the end here are vibrating backwards and forwards quite rapidly. You can hear that sound that it's producing. But to give you an example of the energy that's present in that vibration, we can do a little demonstration. Here is a ping pong ball on a string. I made this last night. And just look at the effect that placing it against the tuning fork has. So even though it's a very quiet vibration, it's still there and it's quite powerful. So this object is moving backwards and forwards, as we said, 256 times per second. And that sound is vibrating, it's traveling out in straight lines from this tuning fork. Not just straight lines in this direction, but also up and down. In fact, it sort of represents more of a sphere where the sound energy is traveling out in all directions until it gets hit, till it hits some other object like myself, absorbs into my clothes or the fabric behind me, for example. So that's a pressure wave. And as I mentioned earlier, what that means is it's a periodic disturbance every 256 times per second. The sound pressure goes up and down, up and down, up and down as those prongs move in and out, in and out, in and out. So when we talk about a wave, that is referring to that energy that is produced by that tuning fork traveling out in all of those directions. But we're not getting, I mentioned that it's a movement of air particles backwards and forwards. It's not really, the air particles themselves aren't traveling across the room. So I'm not firing air particles in all directions. What I'm doing is just transferring the energy from one molecule of the air to the next. Or if it was in water, one water molecule to the next, or in a solid, one solid molecule to the next. So it propagates without causing the medium itself to move. So a wave is a disturbance through a medium by which energy is transferred from one particle in the medium to another without causing any permanent displacement of the medium itself. So each particle will move forward, but then it will return to where it will sort of, if it starts here, it will be displaced, return past where it was, and then come back. So it will oscillate around a particular position. The way it does that is just due to its elasticity. So the fact that it's like when you pull on it and let go, it will return back to its place. Because when that particle has moved, it's left a little gap behind it, which sort of sucks it back in a little bit. All right, now there's a number of different types of waves. One of them is transverse waves. So if we talk about the direction of propagation of that wave, so for example, to you or in this direction, a transverse wave is one in which the waves, the energy is heading in that direction, but each particle is moving up and down at right angles to that direction. So instead of so the energy is going in that direction, but each particle itself is going up and down. I can give you an example of that here with this spring. Can you all see that spring? Now, if I move the spring up and down in this direction, I'm producing a wave that is at right angles to the direction of propagation of the energy. So even though if I go like this, the energy is moving forwards in that direction, bouncing off here and then coming back at me, but each individual part of the spring is moving in this direction. So if you watch carefully, can you see that? It's moving up and down, but the energy is moving in that direction. So it's at right angles. So that is a transverse wave. The other type of wave is a longitudinal wave. And so if I give this a tap, you can see we've got energy traveling in the same direction as the wave. So the wave is represented in this case by each part of the spring bunching up, pulling apart, bunching up, pulling apart like this. And you can watch that wave travel down as I give this a bit of a tap, like so. That's a good example right there. So that there is a longitudinal wave. There's no movement in the transverse direction. It's all in the longitudinal direction. So you're probably familiar with both of those types of waves. So transverse waves are the ones that we encounter at the beach, for example. And longitudinal waves are the ones that we encounter when we're talking about sound. Let's talk about those two waves in a bit more detail. So as I mentioned with the spring, transverse waves are ones where the displacement of the particle is at right angles to the direction of travel. So transverse waves move out from the source of a disturbance. So if you drop a pebble in a pond, for example, those ripples will radiate out from where the pond is dropped. But the individual particle motion, each part of that surface of that water only goes up and down. And so that is a transverse wave. It's perpendicular to that movement. So they're really important in, for example, in the ear. That's how sound moves along the basilar membrane. We have that vibration, which is a transverse wave that's set up on the basilar membrane. But we're going to focus for the rest of this lecture on longitudinal waves, which are the ones that we perceive as sound. Okay, so let's talk about longitudinal waves. So, as I said, sound traveling through air is an example of a longitudinal wave. Another example is, let's say you've got a queue of people and you're all standing there in the queue and someone is in a hurry and they bash into the person at the back of the queue and they bump into the next person who bumps into the next person who bumps into the next person. That is a transference of energy in that direction down the queue, and each person moves in the same direction as that transference of energy. So that's another example of a longitudinal wave. Another example might be a big traffic jam, a queue of cars and someone slams into the back. That transfers energy to the next one, to the next one, to the next one, and so on. So whenever we get a bunching up of those particles or those people or those cars, it leaves a gap behind it or on either side of it. So we get, whenever, we're not creating new particles, so when we bunch up, they've got to come from somewhere, and they come from the areas around them. So we get a bunching up of those particles is called a condensation. And so that's an area of increased concentration of particles, more air molecules, and therefore a higher pressure. So that's an increase in pressure is called a condensation. And the bit where we've got fewer particles than we had before, where we're pulling away from that, where it's less dense, that is what we call a rarefaction. So that's a momentary decrease in the pressure. So I mentioned earlier that if I have something like a tuning fork, so here's a large tuning fork. This tuning fork here, as I strike it, sound will radiate out in all directions from this tuning fork. So that wavefront, you can imagine, is propagating in a sphere around us. So if I strike it, the sound energy moves out in all directions until it strikes an object such as my shirt or the fabric behind us, or the ceiling or the floor, indeed. All right, so imagine that as a spherical wave front moving out in all directions. And what we can visualize that as is areas of condensation and rarefaction, condensation, rarefaction. So the condensation moves out, as does the rarefactions. So it's just those alternating pressure waves. All right, so here's an example of what happens when we have something like a speaker producing sound. So I'm talking into this microphone. These sound waves that I'm producing are being turned into electrical signals, which are being stored in computer systems. And then you're watching this lecture back through some sort of speaker or headphone or something like that. So it's converting the electrical signal that's coming from the sound card of your computer into movement of a speaker diaphragm, which creates sound in the air for you to listen to. So for that to happen, the membrane or the diaphragm of that speaker is being pushed forwards and then pulled back, pushed forwards, pulled back. And it's doing it at the same frequency that I'm producing. So if I was to go, it would be moving backwards and forwards about 1,000 times per second, backwards and forwards, backwards and forwards. When it pushes forwards, it imparts that movement energy into the air molecules that are right in front of it, and they squish up a bit. And that pushes that sound, that energy forwards. And then as the speaker pulls back, it's leaving a bit of a gap. and pushing forward, pushing forward, pushing forward, pushing forward, what we get is a transference of energy in the form of those sound waves outwards from that diaphragm. So let's look at this a little bit closer. If we focus on the wave front shown by the black arrow, you can see that it's moving in a constant direction out from the source. But if we focus on just one of those molecules conveniently highlighted in red here and labeled particle, you can see that it is moving forwards, backwards, forwards, backwards. So each of those red dots don't travel across the room, they just stay where they are, but they move backwards and forwards around their resting position. Whereas the wave energy, shown by the bunching up of those dots or the pulling apart of those dots, is the thing that is traveling. So that is a longitudinal wave. It's movement of individual particles in the same plane as the wave. All right, so what is the simplest form of a wave? What's the simplest type of wave that we can imagine? Well, actually, it's the same type of wave that's produced by a tuning fork, which is a very pure sort of vibration. So if I hit this, you can hear it's producing a very constant, boring kind of sound. And that is coming from the very simple nature of this as an oscillator. It's a mass on a spring. The mass is the weight of the object itself. The springiness comes from where these two prongs are joined together at the base there. And so if I strike it, if I put energy into the system, it is oscillating backwards and forwards, and that sound energy is radiating out in all of these directions. And we can detect that sound energy with, for example, the microphone here and this microphone here. That's detecting that sound that is striking the microphone, the condensations and the rarefactions. But if I was to plot out the amount of condensation and the amount of rarefaction as that changes over time, what would that look like? So if we could measure the change in air pressure at a point in space, somewhere near the tuning fork, that's actually what a microphone does, is it's measuring those tiny fluctuations in air pressure. The condensation and the rarefaction of those air molecules is causing a movement backwards and forwards in the diaphragm of the microphone, which changes the electricity in the wire. It's a very simplified explanation. But if we could look at that over a very short time scale, what would we see? What would be the pattern of that oscillation? Well, we can visualize it in another way using another example of a mass and a spring. So here we have a spring, an actual spring, and here's a mass. It's actually a toy sheep, which I like to use for these demonstrations. But if I release him, gravity is going to pull it downwards. Then the springiness is going to take over, and it will oscillate around that sort of central point about here. And so this is a very simple oscillation. It's in fact the simplest type of oscillation. And we call this a sinusoidal oscillation. It's a sine wave. It may not be obvious to you because it's not moving out, but if I was to walk across the room like so, you would see that it is drawing out a sine wave. Let me walk backwards again. Here it is. We're drawing out a sine wave in space. All right. So yeah, that is a sine wave. What would the waveform look like? It would be sinusoidal. And we call sinusoidal sound waves, we call those pure tones. And that's because they have one frequency. The frequency of oscillation of this guy was about 1 hertz. It was moving up and down once per second. So that's what we call the frequency. We'll talk about that in a bit more detail in a moment. But look, we have areas of increased pressure, increased pressure, and decreased pressure. Condensations, rarefactions, condensations and rarefactions. And if we plot that over time, we get exactly that same sort of wave, a sine wave. Okay, so how can we describe these sine waves? What are some words that we can use to describe its properties? Firstly, we can talk about how close together those wobbles are in time, and we call that the frequency of the wave. For example, here is one frequency. It's moving up and down reasonably quickly. But if I change the properties of the spring, I can change the frequency, and now you can see it's moving up and down at a much lower frequency. So that's how far apart those wobbles are spaced in time. We call that the frequency. How does frequency affect the pitch of a wave? That's an interesting question. Pitch is the psychophysical percept that we have of frequency. So frequency is an absolute measurable property of the vibration of an object. We can just measure how many times it oscillates per second, and that is the frequency of the wave. But the pitch is how we perceive it. And those two things are very, very closely related, but they are not identical. Because there are some situations in the ear, due to the weirdness of the way the ear behaves, that I can have something of one frequency, and just by changing another property of that wave, for example, its amplitude, that might give rise to a slightly different sensation of pitch psychophysically. We'll talk more about that a bit later. Okay, so those wobbles were a certain distance apart in time. We call that the frequency. What about how close together the wobbles are in space? So I mentioned that when I strike this tuning fork, those wobbles are propagating out from the source of that sound. And I'm going to have a condensation here and a rarefaction here, and a condensation here and a rarefaction here. And that distance between one condensation through rarefaction to the next condensation, so from one point of the wave to the same point in the wave, that is the wavelength. So it might be about this big, for example. So wavelength is how far apart the wobbles are in space. Or we could ask, how big is that wave? How large are those pressure changes? In other words, what is the amplitude of that wave? And there are lots of different terms that we can use to describe that. We could talk about it in pascals, in volts, in decibels. What type of decibels? dB, SPL, dBA, dBc. We'll talk about what all of those things mean in a moment. Now, things that are of a greater amplitude typically will sound louder to us as humans. So just in the same way that our perception of frequency is our sensation of pitch, similarly for a sound wave, the change in amplitude will give rise to a different change in the loudness. So the greater the amplitude of a wave, the greater its loudness. But those two things, once again, are not identical. So for example, a wave that is this big might sound quieter than a wave that is this big, because there are two different frequencies and the ear perceives those vibrations differently. So amplitude, at any given frequency, if I increase the size of the wave, it will sound louder. But when I'm comparing the size of waves at different frequencies, they may not have the same perception of loudness. All right, so let's talk about frequency. So the number of cycles per unit time is the frequency. So coming back to our sheep here, that there looks like it's going up and down. It takes about a second to do that. So how many cycles do we have per second? The answer is 1. So it's vibrating at 1 cycle per second. Now, that was the unit of vibration up until the 1950s. We talked about cycles per second, or CPS. We don't do that anymore since we moved to the SI units, the System International. We have units measured in hertz. Frequency is measured in hertz, which just means cycles per second. So 1 cycle per second is 1 hertz. So this is a 1 hertz vibration. If it was 100 times faster than that, I would be fitting 100 cycles per second, would be 100 hertz, and 1,000 would be 1,000 hertz. Another word for 1,000 hertz is 1 kilohertz, kilo meaning 1,000, obviously. All right, so here are some examples of waves of different frequency. Let's play some, just so you get an idea of what waves of different frequencies sound like. So I've got some software here that I use to generate sound waves. So we're going to start out with, let's say, a 1,000 hertz wave. All right, so here you can see on this axis we have the amplitude of those pressure fluctuations. It's going up, down, up, down, up, down. And here you can see the time in milliseconds. So this is 1 millisecond from here to here, 1 more millisecond from here, another. And so this window is showing 5 milliseconds of time. So what is a millisecond? It's 1/1000th of a second. If we take a second and divide it into 1,000 parts, then 1 millisecond is one of those parts. So here you can see that I'm fitting one wave in 1 millisecond, which means I must fit 1,000 waves in one whole second because there's 1,000 milliseconds in a second. That's pretty easy. Let's change the frequency now to be 100. Now I'm going to have to change this here. So if this is 100 hertz, you can see that it's now taking 10 milliseconds for one cycle. And there are 100 lots of 10 in 1,000. And so therefore there's 100 hertz of this oscillation. Okay, so we can do some cool things with the software. For example, let's sweep the sound across the range of human hearing. So I mentioned earlier that we can hear sounds from 20 hertz all the way through to 20,000 hertz. Let's just hear what that sounds like. All right, so you will have heard some of those sounds better than others, and there's a lot of reasons for it. One is to do with this sound system's ability to record those frequencies, how those are compressed in the stream, the video that you're watching. But another contributing factor is your own ears. So for example, you might have noticed that as we were changing the frequency, the amplitude of that wave did not change. It went from -5 up to +5. So the amplitude didn't change, but the frequency was the only thing that was changing. And as I mentioned earlier, the human ear is better at hearing some frequencies than others. So even if your sound system was reproducing that wave at the same amplitude at those different frequencies, you wouldn't be able to hear those very low frequencies all that well. They'd be quite quiet. And then it would sound a lot louder, and it would get a lot louder between 1 kilohertz up to sort of 3 kilohertz. And then it would gradually get quieter and quieter again as it moved to higher and higher frequencies. So I mentioned that a 1,000 hertz wave, we can fit 1,000 cycles in 1 second. And that means each individual cycle takes 1/1000th of a second, or 1 millisecond. If it's a 1 kilohertz signal, each wave, single cycle, takes 1 millisecond. And that is referred to as the period of that wave. So it's the inverse of the frequency. So if the frequency is 1,000 hertz, then the period is 1 divided by 1,000, or 1 millisecond. And you can see that here. So here you can see the period is 1 millisecond. If we double the frequency from 1 kilohertz to 2 kilohertz, then in that 1 millisecond, we're fitting twice as many waves because we've doubled the frequency. So instead of the period being 1 millisecond, it's actually now half a millisecond. So that's 1/2000th of a second, and so on and so forth. If we double the frequency, we halve the period. So what is it that determines an object's vibration frequency? Well, it's an interplay, as I said, between the mass and the stiffness of the object. So for a tuning fork like this, we have a certain mass, as I mentioned, in the prongs, and then the stiffness comes from the junction of those two things. And it's not that easy to play with the stiffness of this particular spring, but I can change the mass, and we'll hear how that sounds. So for example, if I strike the tuning fork, we have this frequency that you can hear. And now what I'm going to do is change the mass by attaching this little weight. So here we go, I'll attach the weight. What happens to that frequency? Okay, so that's with the weight, and then without the weight. Okay, so by changing the mass, I changed the frequency of vibration. What about changing the stiffness? What could I use? Here I've got just a normal sort of desk ruler. And you'll see that this bends quite easily. It's got this certain amount of springiness if I'm bending the whole thing. But if I choose just a small part of it, it's a lot stiffer. So I've changed the stiffness just by bending a smaller portion. So that's very stiff, that's not very stiff. What does that do to the frequency of vibration? If I place the ruler on the edge of this box and just vibrate whatever's left hanging over, we'll get sounds of different frequencies. So for example, can you hear how as I changed the stiffness of this, the frequency changed quite dramatically? You could probably even play a song. That's terrible. Anyway, you get the idea. Okay, so that was frequency. Now what about the wavelength? So if frequency is how close together the warbles are in time, then wavelengths is how close they are together in space. So I mentioned if I strike this tuning fork, those waves are propagating out in space. What is the spatial distance that I could even measure with my ruler between one wave peak going through the trough and then back to the next peak? So what is that distance? And that is the wavelength. So the wavelength obviously depends on the speed of sound in air. So that number happens to be about 340 meters per second if we're measuring at about 15 degrees. So 340 meters per second means that if I strike this wave, if I strike this tuning fork, then the sound energy in 1 second is able to propagate about 340 meters. That is quite fast. It's not super fast because, like, if someone is more than that, if someone is 340 meters away and you see them clap their hands loudly or pop a balloon or fire a starter's pistol or something like that, it will take 1 second for the sound to reach you. So you'll see them do it, and then 1 full second later, you'll hear that sound. So that is the speed of sound. And that obviously determines the wavelength of the sound of a particular frequency, because it's a determinant of how far the wave is managing to travel in space before we reach the next part of that cycle. So the wavelength is the speed of sound divided by the frequency. So as I mentioned, the speed of sound in air is 340 meters per second. So to make these calculations easier, let's think about 340 divided by, let's say, a frequency of 340 hertz. What does 340 hertz sound like? It sounds a little bit like this. Okay, so imagine that sound, 340 hertz. Now imagine I'm standing here producing that sound and you are standing 340 meters away from me. How long does it take for that sound when I produce it to reach you? Well, it takes 1 second because sound travels at 340 meters per second. What's the frequency of the wave I'm producing? It's 340 hertz. So that's 340 cycles per second. So in the 1 second it takes for that sound to reach you, I've produced 340 of those cycles. So between where you're standing, 340 meters away, and where I'm standing here, there's 340 cycles. If you're 340 meters away and there's 340 cycles, each of those cycles must take up 1 meter of distance. Does that make sense? So between you and me, there are 340 cycles. It took 1 second to get there. It's 340 cycles per second. 340 divided by 340 is 1. That's a wavelength of 1 meter. What would the wavelength be if we increase the frequency by a factor of 10? So instead of 340 hertz, it was 3,400 hertz. What does that sound like? 3,400 hertz is 3.4 kilohertz, and that sounds like this. Okay, so we've increased the frequency by a factor of 10. How many cycles are now fitting between you and me? Well, the answer is 10 times as many, 3,400 cycles. So instead of each cycle taking 1 meter, it now only takes, 10 centimeters. So we have increased the frequency by a factor of 10, therefore the wavelength is reduced by a factor of 10. I hope that makes sense. What would it be if we went another factor of 10 higher? If we went up to 34 kilohertz, which is inaudible to human ears, but dogs can hear it. 34 kilohertz, that wavelength would not be 10 centimeters, it would be 1 centimeter. So again, a 10-fold reduction in the wavelength. So there's a handy formula for you to remember that, shown just here. So wavelength is given by this symbol, it's a Greek letter, lambda. Can you see that? Here, this is lambda. So lambda, the wavelength, is c, the speed of sound, divided by the frequency. So here's a way of picturing it. The wavelength is equal to c divided by f. If we make a triangle with c on top and f and the wavelength down here, then we can see the wavelength is equal to the speed divided by the frequency. The frequency is equal to the speed divided by the wavelength. And what's the speed equal to? Well, it's the frequency times the wavelength. All right, so if I know the frequency and I know the wavelength, then that will give me the speed of sound in that medium. So I mentioned it's 340 meters per second in air, but it's actually a lot higher in liquid, like water, and it's even higher in solids like, aluminium or metal or brick or whatever. Okay, so that's the wavelength. What about the phase of the wave? When we say phase, we're really just talking about the starting point of the oscillation. So for example, if I've got my mass on a spring here, if I start at the top, it's going to go down first, then change direction and come back up. If I start at the bottom, where's it going to go? It's going to go up first and then come down. And that is the opposite phase from where we were. If you think about a cycle going up, down, you could also represent that as moving around a circle. So this could be, let's say that this here is 0 degrees, right in the middle. And then we go up is 90 degrees. Down is 180, we're back where we started, but in the opposite direction. We're going down instead of up. This is 270 degrees, and then when we come back, we're at 360 degrees, which is where we started, so 0 degrees again. So it's just like moving around a circle. So 0 degrees and 360 degrees are the same thing. So we're in the middle of the cycle and we're heading upwards. And we can represent the phase in a circular form, and we can talk about that phase difference, as in did we start at the top or the middle or the bottom or the middle but going in the other direction. We can define that phase in terms of degrees of that circle. So if we're at 0 degrees or 360 degrees, that's the same amount. If we're at 180 degrees, then we're at the opposite phase. We're directly opposite the circle than we were. If we're only a quarter of a cycle difference, so if we are at the top instead of the middle, that's a 90 degrees phase difference. So we're sitting at the top of this circle compared to that starting point there. So these two waves that you can see here are out of phase by 90 degrees, but they are otherwise identical. So let me just give you an illustration. I'm going to show you, here's our little mass on a spring. I'm going to let him go, and I'll make two of them, and you'll see that they're both 90 degrees out of phase. Okay, you ready? Here we go. Released. Okay, so this is the same amplitude and frequency, but these two waves are 90 degrees out of phase. What would it look like if they were 180 degrees out of phase? It would look like this. All right, when one goes up, the other is going down, but otherwise they are the same frequency and the same amplitude. All right. Do we need to worry too much about this? Well, yeah, in some ways we do. It's very, very important to do with the way waves interact with each other in a space. The ear isn't very sensitive to phase individually, so if I just present you a single sine wave, you can't tell me what the phase is, but we can use phase differences between the ears, for example, tells us a lot about the directionality of like where a sound comes from. There's all sorts of uses that we can put phase to. For example, this gives us the situation where we can have something called phase cancellation. So if I have one wave that is going up and then down, and another wave that is going down and then up, if they are the same amplitude and frequency and are in the same medium, then those two oscillations can cancel each other out. When one's going up, the other one is going down by the same amount, and the sum of those two things is 0. So if we look at every single point on this waveform, when this is 0, that's 0, the sum is 0. When that's positive 1, this is negative 1. What's 1 minus 1? The answer is 0 when you add those two things together. What's 1 plus negative 1 is 0. Again, here we're back at 0. And here, what's negative 1 plus 1? The answer is 0. So every single data point along here added to here gives us nothing. And the practical upshot of that is that we can use this for noise cancelling headphones, for example. So here's an example of a noise cancelling headphone. You've got a lot more circuitry in here than you would otherwise have for a normal headphone, because what we have is a tiny little microphone on the outside, which is listening to the sound in the environment. It gets amplified and added to the sound that is being played out the speakers. And so we've got sound from the outside world. Let's say it's a bus or a truck or the plane's engines or whatever, some noise that you don't want to listen to. That's coming into your ear from the outside world, slipping around the edges of the headphones. By playing in the exact same sound, but reversed in phase, it will cancel it out. And all you're left with is a much quieter environment in the ear, so that you can hear the thing you're intending to listen to, so your music or an audiobook or whatever, a lot clearer. So that's noise cancelling headphones. Some of you probably are lucky enough to have them. All right. So we can use that for active noise. That's called active noise reduction. We're using energy to cancel noise. And we can also use that as a tool for feedback cancellation in hearing aids. So that you may not be aware, but hearing aids have a microphone where they hear the sounds in the environment and a speaker that plays the sounds into your ear canal. But sometimes sound from that speaker can leak back into the microphone and we get a whistling kind of feedback, a high-pitched feedback, due to the sound that's escaping being re-amplified, and so that's an oscillation. And a lot of hearing aids have circuitry to detect that oscillation, and it plays in a sine wave that's of the opposite polarity to cancel it and quench that feedback. So that's a very handy tool for people who get feedback in the hearing aids. All right, now we're going to talk about the amplitude of the wave, the bigness of the wave. And as I mentioned, sound is a fluctuation in atmospheric pressure. And the unit for pressure is the Pascal. PA is the symbol. It's named after Blaise Pascal, this mathematician and scientist that you can see on the picture there. And 1 Pascal of pressure is equivalent to 1 Newton per square meter. So if we imagine this is like a square meter, if I applied a force of 1 Newton, that would be 1 Pascal. What's a Newton, you may ask? Well, Isaac Newton is obviously the famous scientist. But 1 Newton of force is the same amount of force exerted by a 102-gram weight due to gravity. So gravity is accelerating this weight down. If the weight was 102 grams, it would be accelerated downwards with a force of 1 Newton. So if we apply 1 Newton over 1 square meter, that is a pressure of 1 Pascal. That seems like a reasonable amount of pressure. You can picture what 100 grams of something feels like, and that's spread out over a meter. That's 1 Pascal. How much pressure are we under right now? And I don't mean the pressure of you being in this course. I'm talking about atmospheric pressure. How much of that are we experiencing right now? Well, the answer is it's a lot. Atmospheric pressure is 101,300 of those pascals that we're experiencing right now. It's pressing in all around us. So you might have heard, we would say 101.3 kilopascals. In a weather report, they might use the word hectopascals. They might say 1,013 hectopascals for people who don't like decimal points. And so, yeah, that standard atmospheric pressure is 101,300 of those. And that, as I mentioned before, that pressure is relatively static or unchanging. It might change with the weather a bit, up and down. And sound, as I said earlier, is an incredibly, incredibly tiny wobble on top of that static pressure. And the quietest sound that most people can detect is the equivalent of 1/2 of atmospheric pressure. So it's an infinitesimally small variation in atmospheric pressure, 1/2 of atmospheric pressure we can actually detect with our ears, which is pretty remarkable. And the scale of pressures that or amplitudes that our ear can cope with is also quite remarkable. So if the threshold of detection of sound is a very, very tiny wave, but as we make that amplitude larger and larger and larger, it will sound louder to us, but it will reach a point where it sounds painfully loud. And we call that the threshold of pain. So what we call our dynamic range of hearing is from the threshold of detection up to the threshold of pain, where it's too loud for us to tolerate. That difference in pressure is actually a millionfold difference in pressure. So if we've got a wave that is this big, at the threshold of detection, then imagine that a million times larger. That's how big of a wave our ear can cope with before we start to feel pain. So that's a remarkable range of amplitudes for us to detect. So as a ratio, what is that? Let's think about that in physical terms. What would that be like? So the threshold of hearing, as I said, is a very small amount of atmospheric pressure. It's actually what we call 20 micropascals, 20 millionth of a pascal. RMS, I'll talk about what RMS means in a moment. And then the threshold of pain is a million times larger than that. So that's not 20 micropascals, but just 20 whole pascals, 20 pascals RMS. And that's a ratio of 1 to 1,000. That is equivalent to the weight of one mouse compared to 4 elephants. I'm not sure whether they're African or Indian elephants, but I'm assured that the weight of 4 elephants is about 19 tons compared to the weight of one mouse being 19 grams. And that's a ratio of 1 to 1,000,000. So the little mouse is representing the quieter sound we can detect. The 4 elephants is representing the loudest sound that we can tolerate. Okay, so those magnitudes are obviously really unequal. And how do we cope with that when we're trying to write down those numbers on forms? If I had to measure hearing thresholds of someone with really perfectly normal hearing compared to the hearing thresholds of someone whose hearing was closer to that threshold of pain end, so that let's say they had a profound hearing impairment, and I had to make the sounds a million times greater in amplitude for them to detect it. Can you imagine an audiogram where some of the numbers are around the 1, 2, 3, 4 mark and others are around the 900,000 to 1,000,000 mark? That would be a very, very big chart of paper in order for us to have any sort of detail at both the small end and the large end. It would be quite difficult. I like this comment, for example. This is an XKCD comic showing the amount of fuel energy density in megajoules per kilogram, and you can use a sort of a bar chart to represent those numbers. So we've got sugar at 19, coal at 24 megajoules per kilogram, fat at 39, gasoline at 46, and then uranium at 76 million. And so this is a representation of how big the bar on that bar chart would have to be to cope with that unequal magnitude. Well, the answer is that is a silly choice. That's a linear representation of those numbers. We can get around that by using what we call a logarithmic scale. And so rather than going up in magnitudes that are additive, so 1 plus 1 is 2, 3, 4, 5, 6, 7, 8, 9, 10, we can go up in steps that are multiplicative. So 2, 4, 8, 16, 32, 64, for example, or 1, 10, 100, 1,000, 10,000, 100,000, 1,000,000. So we've covered that range from 1 to 1,000,000 in only a small number of steps. And that's much easier to represent on a chart. So the unit that we use that uses a logarithmic scale is the decibel. It's named after Alexander Graham Bell, who you might be aware of as the sort of the inventor of the telephone. The decibel is a unit of the measure of a ratio between two quantities. It could be energy, it could be pressure, it could be any number of things you could apply a decibel scale to, and we do, but in our context we can be talking about sound pressure or the voltages that are producing, resulting in that sound. So a decibel is a measure of the ratio between two quantities. It's not an absolute thing, it's the ratio of one reference, and you're saying, well, here's our reference. Let's say something is 10 times as big as that, or 100 times as big as that, or 1,000,000 times as big as that. We can use a number to relate that new quantity back to our original quantity. And so the size of the original quantity will differ depending on what it is that we're talking about. Okay, so for example, the way we calculate it is like this. So a pressure ratio in decibels is 20 times log to the base 10 of your pressure compared to that reference. So if here's the pressure I'm interested in, I can say, well, how much bigger is it than this original thing? And if your answer is, well, it's 1,000,000 times bigger, then that is the blue part there. Pressure divided by the reference is 1,000,000 divided by, let's say, 1. So 1,000,000 divided by 1. And then we take the log of that. Now, a lot of you at this point are going to be going, logs. I thought once I was out of high school, I was free from logs. The answer is we're going to talk about them a bit, but they are probably a lot simpler than you remember them, hopefully. So most of you will have a calculator on your phone. I'll just quickly show you how to do a log calculation. All right, so on your phone, if you go to the calculator, you're probably used to this sort of view where you've got the numbers, but if you turn it sideways, like so, you end up with the scientific version here. So if I said that our pressure ratio was 1 to 1,000,000, that's 1,000, that's 1,000,000, and I wanted to see what is the log of that, there's a button here, log to the base 10, and I press that, and the answer is 6. So the log of that ratio of 1 to 1,000,000 is 6. What you might notice about the number 6 is it also is the number of zeros that are in 1,000,000. So we've got a 1 followed by 6 zeros. So that's a really easy trick that we can use when we're dealing with decibels that are a factor of 10, is that we can just count the number of zeros, and that helps us do the log of that particular number. So what would be the log of 1,000, do you think? The answer is 1, 2, 3 zeros. The answer is 3. What's the log of 10? How many zeros are there? There's 1. Log to the base 10 of 10 is 1. So the inverse of the log is when we raise something to the power of something else. So to the power of 10. So 10 to the power of 1 just means we've got 1 10. So if I go 10 to the power of 1 is 10. 10 to the power of 2 is 100. So another word for 10 to the power of 2 is 10 squared. 10 times 10 is 100. What's 10 times 10 times 10? That's 1,000. So how many zeros are in 1,000? The answer is 3. What is 10 raised to the power of 3? The answer is 1,000. So we can move forward and backward between logs and the exponent raising 10 to the power of something. Okay, so that's the log part. What about the rest of this formula? We have to multiply that result by 20 to get our ratio in decibels. So if we're talking about our factor of 1,000,000, log to the base 10 of 1,000,000 is 6, because there's 6 zeros. 6 times 20 is 120. So a pressure difference of a factor of 1,000,000 is a 120 decibel difference in that sound pressure. And that corresponds to the dynamic range of human hearing. So if you think about an audiogram, it goes from 0 decibels down to 120 decibels. That's because it covers the range over which humans can hear. So from 20 micropascals to 20 pascals, or from 0 decibels to 120 decibels on that particular scale. So another way of saying that is it's 20 times log to the base 10 of how much bigger one pressure is from another pressure. And that is really convenient for us as audiologists and speech language therapists to specify sound pressures which change over a very, very large range. So as I mentioned earlier, the loudest sound we can tolerate is at least 1,000,000 times larger in amplitude than the faintest sound you can detect. And it's much easier to write that ratio of 1 to 1,000,000. That's a linear ratio. It's much easier to write it as 120 decibels, because 20 times log to the base 10 of 1,000,000 is 20 times 6, which is 120. The other advantage is that logarithmic scales better reflect our perception. So the quieter sound you can hear compared to the quieter sound you can tolerate, it doesn't sound 1,000,000 times louder. It's some number much, much less than that. And so our neural firing rate for most of our senses varies over a logarithmic range of intensities. So as the thing we're trying to measure increases linearly, the output of our nervous system changes in a more logarithmic fashion rather than in a linear fashion. Okay, so that was one trick. I've just shown you the count the zeros trick. Let's go into that in a bit more detail. So trick number one is if it's a multiple of 10, count the zeros and then times it by 20 for our decibel formula. So if I multiply something by 1, I'm increasing it by a factor of 1. How much of an increase is that? Well, it's not an increase at all. There's no change. So that's a 0 decibel change. Does that make sense? So multiplying it by 1 is a 0 dB change. How many zeros are there in 1? The answer is none. So count the zeros. There's no zeros. Times that by 20, still 0. That's 0 dB. So what about if I make something 10 times bigger? Count the zeros. We've got one of them. 1 times 20 is 20 dB. So if something's 10 times bigger, it's 20 dB larger. What about 100? Can you do that? 2 zeros, 2 times 20 is 40. The answer is 40 decibels. And 1,000 is therefore 60 decibels. All right, so that is the first trick. The second trick is that if you're multiplying by something that is less than 1, then the decibels are negative because we're taking away amplitude. It's getting smaller and smaller. So just as we said that if we're multiplying something by 1, it's a 0 dB increase. If I'm now making it 10 times smaller, 1 on 10 is 0.1. And so whereas when I made it 10 times bigger, it was 20 dB, 10 times smaller is minus 20 dB. Now, you can see how that makes sense. I've got an object, I make it 10 times bigger, it's now 20 dB bigger. If I make it 10 times smaller, I'm back to where I started from. So I take away 20 dB. So if I'm going from some size to something that is 10 times smaller, I'm removing 20 decibels from its amplitude. All right, so similarly, if I'm making it 100 times smaller, it's not plus 40 dB, it's minus 40 dB. If I'm making it 1,000 times smaller, it's not plus 60 dB, it's minus 60 dB. All right, so that's the second tip. The third trick is the doubling trick, which is every time you double it, you add 6 dB. So if I've got a quantity that is 1, and it's 1 times as big as it was before, that's no increase at all, it's a 0 dB increase. But if I now double it, and now it's 2 times as big, that's a 6 dB increase. If I make it 2 times as big and then 2 times as big again, that's another 6 dB increase. If I make it 2 times as big again as what it was just then that's another 6 dB. So every time I double it, that's 6 dB. So you can see how this number is getting much, much bigger, but the decibels is only incrementing in 6 dB steps. So I'm going from 1 to 2 to 4 to 8 to 16 to 32, 64, 128. In decibel terms, I'm only going 6, 12, 18, 24, 30, and so on. And so it's a much slower increase, which is really great. So let's read across each of those lines there. So a factor of 2 is 6 dB more than a factor of 1. A factor of 20 is 6 dB more than we had for a factor of 10. So instead of 20 dB, it's 26 dB. So instead of a linear increase of by 100 being 40 dB, if it's by a linear increase of 200, then that's 40 plus 6. The answer is 46. Okay, what about this one? This is 0.2. So remember, if it's less than 1, it's going to be negative decibels. What was our answer for 0.1? So that's this one down here. You can see if 0.1, a 10-fold decrease is minus 20 dB, 0.2 is only a 5-fold decrease. So it's going to be 6 dB larger than our minus 20. So what is minus 20 plus 6? The answer is minus 14. So you can just mix and match these things. Every time we're increasing by a factor of 10, we're adding 20 dB. If we're doubling, we add 6 dB. If we're making something smaller by a factor of 10, we're taking away 20 dB. What happens if we halve something? Well, instead of adding 6 dB, we just take away 6 dB. So a half is 0.5. 20 times log to the base 10 of a half is minus 6. What about this case here? So we're essentially reading across, it's half of this one here. If I take 6 dB away from minus 20, what do I have? I have minus 26. What about this one? 50. So 50 is half of 100. So if 100 was 40 dB, if I take away 6 dB from that, what have I got? 40 take away 6 is 34 dB. And what about log to the base 10 of 500? Well, you might recognize that 500 is half of 1,000. 1,000 is 60 dB, and so 6 dB less than that is 54. There we go. So these two tricks are, well, 4 tricks are pretty simple and come in handy when you're thinking about decibels. Okay, so when we're talking about decibels, we're talking about ratios. Something can be larger than something or smaller than something. If it's larger, it's a positive number of decibels. If it's smaller, it's a negative number of decibels. Easy peasy. Here are some standard ones that are variations of what we showed you in the previous slide. So for example, increasing something by a factor of 1,000, you're adding 60 dB. If you're decreasing something by a factor of 1,000, you're taking away 60 dB. That's minus 60 dB. So when I say a ratio, I mean something relative to something else. And when we're talking about sound, we're talking about an amount of sound that could be this big or this big compared to some reference amount of sound. What number do we use as that reference? Well, it really depends on the flavor of decibels that we're talking about. So one common one that you'll come across is sound pressure level, or dB-SPL. And that's really a physical measurement of the properties of a sound. It doesn't take into account human hearing at all. It's a physical quantity that you can measure with equipment like microphones and sound level meters and all those sorts of things. So it's not, it's a physical quantity. It's not related to human perception, except for one factor, and that is that the reference happens to be chosen to be the threshold of human hearing at 1,000 hertz. So the average human threshold, the average human sensitivity for hearing is about 20 micropascals RMS. I'll just take a moment here to tell you about what RMS means, and this is a really cut down version, but it's really a way of describing the amount of energy that's in a signal. So imagine we've got 2 waves. Here is the baseline. This is 0 amplitude, so that's no displacement here and here. But this wave goes like this, above and below. Pardon my dodgy sine wave there. And this one here is a lot smaller here, but then has this one little bit where it's larger, and then the rest of the time it's much, much smaller. Now, how do we measure the various amplitudes of these 2 waves? Well, one measure is the peak amplitude, and so that is how far is this from 0 at its maximum extent, which is about here. How far away is it from 0? That's its peak amplitude. But can you see how this one is larger in that direction than in that direction? So a different measure we can use, which encompasses any asymmetries, is peak. So that's peak. And this one measured from here to where it reaches at the bottom end is peak to peak. So that's peak to peak. And that's both of those are totally valid ways of measuring the amplitude of a sine wave. Now, what about this wave here? What's its peak to peak amplitude? Well, that stretches from here to up here. So that's its peak-to-peak amplitude is like that. So out of these 2 waves, which has the largest peak-to-peak amplitude? The answer is this one. But which one carries the most energy? And by energy, what we mean, another way of saying that is which one spends the most time away from 0, away from the no energy state. And the answer is this one does. So this one is carrying more energy than that wave there. If I was to pass, if these were electrical waveforms and I was to pass both of them through a light globe, I'd get far more light from this signal than I would from that signal there, because it's close to 0 most of the time, except for this brief moment here. So you don't need to know this, but what we do is calculate what we call the RMS amplitude, or the root mean squared amplitude, which gives us that indication of how much energy is in the waveform. So the way you do it is RMS means it's the square root of the average, the mean, of the square of the waveform. So you square it, you take the average of the square, and then you take the square root of that. You don't need to know this. Just reiterating that point. So if I was to multiply each of these values by itself, 1 times 1 is 1, minus 1 times minus 1 is positive 1. So I end up with something that is always above 0, and it would look like that. What's the average value written across here? Well, it's about that. And then I take the square root of that, and that gives me my RMS amplitude, which is here. Now, what about this particular situation? All of these ones, I do exactly the same process. I square it, multiply it by itself, and then take the average. And the answer is it's basically nothing. And then I go above 0, and then above 0 again, and then it's basically nothing the whole rest of the time. And what's the average value measured across this whole period? The answer is basically nothing, and then I take the square root of that and it's basically nothing. So the RMS amplitude of this wave is far greater than that wave. Okay, that is all I will say about RMS amplitude for the moment. So by saying 20 micropascals RMS, we're not tying ourselves to a sine wave. We're talking about any wave that has that amount of energy. And waves, as we'll talk about soon, have all different properties. They're not just sine waves, they can be complex waves as well. Okay, so dB SPL means decibel sound pressure level, and that's just, we just use a reference of 20 micropascals RMS as our reference. So the SPL scale is a physical descriptor, an absolute physical descriptor that is without reference to humans, other than the fact that that 20 micropascals RMS represents the threshold of human hearing for a bunch of young adults at 1 kilohertz. If you measure all of those people's thresholds, the quietest sound they can typically hear is about 20 micropascals RMS. And so that was chosen as the reference. So at any frequency, 0 dB SPL is 20 micropascals RMS. And if we go a million times larger than that, then it's 120 dB SPL, for example. Okay, so I mentioned at any frequency that is 20 micropascals RMS. That isn't very useful on an audiogram, for example, because humans are much better at hearing 1 kilohertz than we are at hearing, say, 200 hertz or 8 kilohertz. It takes a lot more energy to stimulate the ear at those frequencies. So we need to put more pascals in to achieve the same effect, which is our threshold. So to compensate for that, we've developed a different scale. I say we. Psychophysicists of the past have developed the dBA weighted scale. And so that compensates for the fact that humans hear some frequencies better than others. And that is best used for measuring quiet sounds. There's another weighting scale called dBC, which is more suited to human hearing at very high levels. And then we have a totally different scale, which is dBHL, and that is what you have on the audiogram. So that's down the y-axis of the audiogram is decibels hearing level. And what that is vaguely similar to dBA, but it's very specifically measured at audiometric frequencies. And what it means is that for any frequency, the average human hearing threshold is adjusted so that that's sitting at 0 dB HL. So 0 dB HL at 250 hertz is the average human threshold at that frequency. At 1K, it's the average human threshold. At 4K, at 8K, at 16K, it's the average human threshold for people with what we define as normal hearing at those frequencies. Okay, so it's just we've shifted all of those things so that a flat audiogram means you've got no hearing loss at any of those frequencies. Otherwise, it would be curved, and that curve would look something like this. So imagine showing someone this and saying, this is your hearing and it's totally normal, when in fact you can see, oh, at low frequencies, my hearing's really bad. I need 70 dB SPL in order to hear something at 20 hertz. The answer is, well, that's totally normal. Everyone's looks like that. And you'd be having all sorts of conversations with your clients saying, oh yeah, this curve is right, but that curve is slightly the wrong curve. So the way we get around that is we take that red line and flatten that across at 0, and that becomes our dBHL curve. So as I mentioned earlier, we can hear between 20 hertz and 20,000 hertz, but we're not equally sensitive across those frequencies. So for example, here it takes a lot more pressure to stimulate down at these low frequencies than it does at the mid frequencies. So if we look here at 30 hertz, this is a logarithmic scale, so that's why these numbers aren't equally spaced. 10 hertz, 20 hertz, 30 hertz. Human hearing at 30 hertz is really quite poor, and therefore if I put in 70 decibels of sound pressure level, I'm 10 dB above threshold. That is the same as me being at 10 dB SPL at 1 kilohertz. So just to say that again, 70 dB SPL at 30 hertz will sound the same to us as 10 dB SPL at 1 kilohertz, even though the 30 hertz tone is 1,000 times larger in amplitude, 60 decibels larger in amplitude. So to get the dBA scale, we just subtract this red line off and it becomes a flat line. So that is the dBA scale. It really defines everything in terms of how far above human threshold it is. This is really important for things like machinery noise, for example. If something is putting out 70 dB, that may not worry us at all because it's at a frequency where we're not very sensitive, or it could be right there at 1 kilohertz and we'd be very sensitive to it. So it's really a good tool for using to measure the degree to which something can affect us in terms of hearing loss, but also in terms of just how annoying it is. All right, so when do we use decibels? Basically, we can use them whenever we need to communicate a sound level. So this includes hearing thresholds for pure tones. When we're talking in the audiogram, we're talking in decibels. If we're talking about speech reception thresholds, we also can measure those in terms of decibels. We might use the dBA scale because that, again, adjusts the different frequencies in speech relative to how well we can hear them. We might use decibels and again the dBA scale, hopefully, to measure the sound levels that we find in a classroom. We might be able to specify that the sound shouldn't be more than this number of dBA for it to be a good listening environment. And we can also use decibels when we're talking about signal-to-noise ratio. So signal-to-noise ratio means that the signal is this amplitude and the noise is this amplitude. And if they are the same amplitude, then it's a 0 dB signal-to-noise ratio. If the noise is twice as big, then it's a -6 dB signal-to-noise ratio. If the signal is twice as big as the noise, that's a +6 dB signal-to-noise ratio. Do you get that? So we'll talk more about each of those in a moment. So when I'm talking about things like background noise levels and things like that, we usually measure those things with a sound level meter, which is basically just a microphone connected to some signal processing circuitry and then some sort of output, which tells us the level of the sound that's in the environment. And there are a number of different types of sound level meters. I've got one of them here. You can see right here, it's got a microphone at this end and then a display here for reading off the sound levels that are measurable in the room. There are a number of different types. So the first type is a type 1 sound level meter, which is for precision measurements that are typically carried out in laboratory environments. And the other type are type 2 sound level meters like this one here. So this one here is a type 2 sound level meter. It's used for field measurements. I'll just show you on the document cam. You can see here it says type 2 sound level meter. And they each have a range of different buttons that are fairly similar across all the different types. So one of the things you'll notice is it has a choice between the weighting function that is used. So A weighting is one that matches human perception at very quiet levels up to about 50 dB SPL. And then beyond that, human perception, that very steep-looking red curve that I showed you a few slides ago, tends to flatten out a bit for very high sound levels. So we tend to perceive sound pressure levels a bit more evenly at the very high levels. And so we use a different weighting for measuring very loud sounds, and that's the dBc weighting. In between those two, the A and the C, is a dBb weighting, which sits around the 70 dB SPL mark. But in practice, that didn't get used very much. It was typically you use A for everything that's not super loud and C for everything that is quite loud. And so that's typically the two choices that you've got. So for example, here you can see with an A weighting, it's measuring my voice at levels that sort of most approximate typical conversation levels. But if I was getting much, much louder, I might want to use a C weighting, and that boosts the effect of the low frequencies and the very high frequencies. Because, as I mentioned, our perception is much flatter at those levels. I'll stick it back on A for the moment. The other key option we have here is the integration time. So we can choose between a fast integration time, which is about 125 milliseconds, or a slow one, which is about over a second. And the difference between those two really is important when we're wanting to measure the levels of sort of individual utterances. So any pause, we're going to drop back to baseline level between those two. So for example, I'm talking now and then I stop. And you can see we dropped back down to the sort of about 48 dBA noise level in this room. If I just wanted to ignore any pauses and just give an overall level, what I would do is switch to the slow rating that you can see here. And now the integration time has changed to 1 second. So it smooths out all of those bumps. And if I pause for a second, it doesn't drop down anywhere near as much. It still drops down, but it handles tiny pauses quite well. And we don't see as big of an effect there. Okay, so I'll stick it back on fast. The other thing to look at is this range setting here. So if I'm interested in measuring very quiet sounds like the background noise level in this room, I'll put it on this 30 to 70 range. I'll be quiet for a moment so you can see what it is. It's about 41 dB. Normal conversational speech would be covered by the 50 to 90 range. And then if I was trying to measure very, very loud sounds, I'd probably switch to a dBc rating and the 90 to 130 range that you see on there. Okay, back to our resting spot. I'll just leave that there. So sound level meters are really useful, obviously, but they do cost money, and that might limit their usefulness or their ability or how widespread that they can be, and fewer people are able to measure the sound levels in their environments. So to get around that, there's been a proliferation in recent years of sound level meters that are built or that run as apps on smartphones, and they're able to take advantage of the standardization that occurs in components that are produced in smartphones. So for example, if you take any particular model of iPhone, they'll all use the same microphone that's amplified by the same amount and will give basically pretty much the same output within a certain number of decibels. So all you need to do is write a smartphone app as a sound level meter, calibrate the sound levels that you would record from each of the different models of phone, say for example all of the different iPhone models, build those calibrations into the app and then release it on the market, and they actually produce pretty good results. So there was a paper, obviously there's lots of these things, but there was a paper in 2014 that looked at 192 sound level meter apps and found only 4 that met their criteria, and one of those is this one by the NIOSH, the Occupational National Institutes of Occupational Safety and Health in the United States, which gives results within plus or minus 2 dB from a reference type 1 sound level meter. So I strongly suggest getting a hold of one of these. If you've got an iPhone, this app is a good one. There are other validated apps, I think, for Android-based phones. For example, I mean, they're really useful. I use them all the time. So at gigs or something, it might be very, very loud and you just want to check just how loud is it. You can use it for that. There's a lot of cicadas outside at the moment. I was standing under a tree and it was really loud. And so I was able to measure the sound level and hear just to get an idea of what that sounded like. So it's a great app. I thoroughly recommend you download it. I'll put a link on the Learn page. All right, so now I'm going to talk about some more in-depth analysis we can do of sound, where we're not just looking at the overall level of a sound with a sound level meter, but we can look at the different frequencies that are making up that sound. So I guess an equivalent would be to have a light meter that tells you whether it's light or dark, but it doesn't really tell you what colors are present, whereas spectral analysis would. And that tells us the frequency content of the signal that we're looking at. So just as you can use a prism to break a white light into a spectrum of different lights from the reds, low frequencies of light up to the higher frequencies of blues and purples, we can also break sound up, or any signal, into its component parts. The person first responsible for defining the mathematics around this was Joseph Fourier. Here's a picture of him here. And that technique is very long and cumbersome and involves pen and paper in his day, but we have now got computerized versions of this task, and in particular an algorithm called the fast Fourier transform. The fast Fourier transform sort of has really progressed signal processing and made it far more accessible, and it's now the idea of decomposing a signal into its frequency components, doing stuff on it and then getting it back into a waveform is incredibly widely used. It's how you're hearing me now, for example. The audio I'm producing is being compressed to make it a smaller file size, and that's involving FFTs and inverse FFTs and all that sort of thing. So if we look at these two waves that you see here, this is the time domain representation because we have time on the x-axis, and this is the frequency domain representation because we have frequency on the x-axis. We have voltage on the time domain waveform, and you can see that this wave goes up and down by a certain amount, so it's got a certain amplitude. This wave down here goes much higher and much lower, so this has got almost double the amplitude of this particular wave. Can you see that there? So that they differ in terms of the amplitude. These two waves also differ in terms of their frequency. The bottom wave has a higher frequency than the top wave. What's the third thing that we need? We've got amplitude, frequency, phase is the other thing that we use to describe a sine wave. And so what we see here is that the phase of this bottom wave, it starts at 0 and goes up, whereas this one starts at 0 and goes down. So these two things are out of phase by 180 degrees, these two waves. So what we have here is the time domain representations, and you can clearly see those differences. What about if we plot it in the frequency domain? So in the frequency domain, we can read off here that this is a particular frequency and a particular amplitude, and this wave here has a higher frequency and a higher amplitude. What you're not seeing on here is the phase, but the phase is absolutely critical to a full description of that time domain waveform. So if I have a phase spectrum of this, looks exactly like this one, except instead of amplitude here, it's phase. So those two things would differ by 180 degrees in this case. All right, so the beauty between the time domain representations and the frequency domain representations is that they are 100% equivalent. They're showing us exactly the same information. If I've got a time domain waveform, I can see the frequency, the amplitude, and the phase. And if I've got a amplitude spectrum and a phase spectrum, I need two graphs, amplitude spectrum and phase spectrum, that is the same information that was shown in the time domain representation. And I can flip forwards and backwards between those two. So to get from the time domain to the frequency domain, I do a fast Fourier transform. To get from the frequency domain back to the time domain, I do an inverse FFT, an inverse fast Fourier transform. Okay, so to keep things simple, so far I've been talking mainly about sine waves because they consist of one frequency component, and that's visible on this frequency domain representation. You can see we've got a line that's only at one frequency in each of those graphs. But things get a bit more complicated when we move away from sine waves and move away to more realistic sounds that we get in the environment. And the opposite of a simple pure tone like this is a complex wave. So my voice, for example, is a complex wave, and it has energy at a whole variety of different frequencies. Let's just have a look at the spectrum of those and see how they differ. Okay, so what I'm going to do is generate a 1 kilohertz sine wave and then look at the spectrum of that as it's being picked up by the microphone of the computer. Now, it's also going to pick up my voice. So what you'll be seeing is when I'm not talking, you'll just see the sine wave, which is sitting there in the background. But otherwise, you will see my voice. And you'll see at the top of the screen will be the time domain, and at the bottom of the screen will be the spectrum. So here's our 1 kilohertz sound. Okay, I've paused that just so you can hear me properly. There you can see that 1 kilohertz waveform, and here is the spectrum. So if I slide my little slider along here, what's the frequency of that peak? You can see that that peak is at exactly 1000 hertz. So that is a 1 kilohertz spectral peak. All of this stuff down here is the background noise. I'm going to resume without the sine wave playing now. You'll see that 1 kilohertz peak will disappear. But what you'll also see is all of the sound energy that's contained within my voice. So let's resume. So you can see that 1 kilohertz peak has disappeared. But now what you can see is all of the energy that is present in my voice. So this top waveform here is the time domain representation. When I make a vowel, you'll see that it's lots of low frequency content. So if I go, it's a repetitive low frequency content. If I make a hissing sound, it's more high frequency energy, and the lines move much more rapidly on the screen here. So if I go shh, so when I go shh, there's energy at the high frequencies. When I make a vowel, there's energy at the low frequencies. What's the relationship between these two? Let me again make a vowel sound like an R, and then I'll press pause and we can measure some of its properties. So there we go. I made the R sound. I'll do it again. Right. I hope you don't mind me going Here is the sound that I generated. Let's zoom in a little bit here so we can see it a bit clearer. 0.05. Okay, so here it is, and you can see it's a repetitive wave. Can you see we've got a peak here, then another peak, then another peak, then another peak? So this pattern from here to here is repeating. And that's because it's a harmonic complex. It's made up of a fundamental frequency and multiples of that frequency. So it's got multiple frequency components. Let's have a look and see what they are. So the first one is we've got this main feature that is repeating itself here, 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 here. And the time delay, let's measure that. So this first peak here is about 21.6 milliseconds. The second peak here is at about 31.6 milliseconds. So they are 10 milliseconds apart. So the period of that wave is about 10 milliseconds. And remember, frequency is 1 on the period. So that corresponds to a frequency of about 100 hertz. So if we look on the frequency domain representation, where do we see that main spectral peak? Here it is here at 100 hertz. So I'm producing a 100 hertz, a vowel with its fundamental frequency at about 100 hertz, and you can see that there. Now, there's a number of different spectral peaks here that are present, and they are at multiples of 100 hertz. So this second peak here is at 200 hertz. We've got another one here at 300 hertz, 400 hertz, and so on. Now watch what happens to those peaks as I shift my fundamental frequency. If you excuse me, it's going to sound a bit silly, but shift my fundamental frequency from 100 hertz to higher frequencies and back. You should see those spectral peaks spreading and contracting in the frequency domain. As we go to higher frequencies, they'll get further and further apart and then come back down. In the time domain, what you'll see is they'll bunch up closer and closer together because they've got a shorter period. As the frequency increases, the period decreases. So let me resume that again. Anyway, that sounds ridiculous, but there you go. I'll reset this amplitude. There we go. All right, so, and also you should be able to notice the difference between quiet sounds and then very loud sounds. You can see the difference in the amplitude of how I was talking there. So that speech waveform was made up of not just the fundamental frequency, but lots of higher harmonics. And the combination of those harmonics at different levels all contributes to that feeling of the timbre of the sound. So how is my voice different from someone else's voice? And the relative amplitudes of those frequency components was also what dictates our percept of the particular vowel that's being spoken. So that was an R vowel, but watch when I change from an R to an E to an OO, what you'll see is the shape of those spectral peaks will also change. All right, so that's one way of looking at it. There's another way which is a bit more, you might find a bit more intuitive, and that's a spectrogram. So some of you might be familiar with the Chrome Music Lab that you see here. There's all sorts of tools that you can play with. I'll put a link on the Learn page. But today we're going to look at this one here, the spectrogram. It's a bit more fun than the type of spectrogram you'll be using for phonetics and for your speech analysis as part of your speech and language therapy degree. But I really like this one because it shows a number of things simultaneously. So just as we had frequency on the x-axis of our spectrum, in spectrograms and spectrographic representation, we have low frequencies at the bottom of the screen and higher frequencies at the top of the screen. So we've sort of flipped from that arrangement to that arrangement. The other thing is that as we move through time, the spectrum changes and it sort of paints across the screen. The other thing is that high energy is given by darker, sort of like brighter, redder colors here, showing more energy compared to lower energy. And in this particular one, they point so that it's like they're protruding out of the screen, which I quite like. So here you can see the spectrogram of my voice. Let's try that vowel shift again. So obviously it doesn't have the fine-grained detail that the typical speech therapy style spectrogram would have, but it does look cooler, you must admit. Let's try that whistle. And let's try our tuning fork. So look at that, beautifully pure for the most part. When I initially struck that, did you hear there's an overtone, like a higher frequency component that's also visible? And that shows up at one multiple of the tuning fork above. So here we go. You can see it just dying out there. There's the fundamental and there's the higher harmonic there. All right, so download this and have a play. It's really cool. By the way, spectrographic analysis is incredibly useful for a whole variety of different sound analyses. Here's one. Instead of using a microphone, what you can do is listen to sort of bird chirps. Very cool. All right. Okay, so here's a cool animation showing you breaking up of a complex sound into its different frequency components. So here the red line is actually composed of the summation of all these little blue signals, and they're all at different frequencies that are multiples of that original. So as we spread each of them out on a frequency axis, if we take them out there, you can see going from low frequencies to higher frequencies. It's basically we're making up that red line by the sum of the first wave at that amplitude, the second wave at that amplitude, the third one, the fourth, the fifth, and sixth harmonics, all at decreasing amplitudes. And you add them all together and you get this pattern, which is fairly squarish. We call that a square wave. Let me show you some other examples of square waves and related signals. So here's a 100 hertz sine wave. Here you can see we've got a spectral peak at 100 hertz. If it was at 1000 hertz, it would look like this. But we're not, we're at 100 hertz, and this is a sine wave. You can see it's beautiful and sinusoidal. Let's change that to a square wave, and you can see to get our waveform looking nice and square, it has to be made up of all of these different harmonically related components. So this is at 100 hertz. We skip 200. This is 300. 500, 7, 9, 1100, and so on. So all of the odd harmonics are present here that are making up this, this square wave here. There are all sorts of other shapes of repetitive waves that are simple sort of waveform shapes that you can find. Here's another one, which is a sawtooth wave. And instead of all the odd harmonics, it's actually odd and even harmonics. We've got 100, 200, 300, 400, 500, and so on. A sawtooth is sort of the sound that you would get when you're dragging a bow across a violin. So if you look at that time domain representation, the bow grabs the string, lets go, grabs, lets go as it's moving past, sort of slips like that. And you can hear that in the sound. I'll turn it up a bit. I mean, it doesn't sound very much like a violin, but okay, it doesn't sound too much like a violin, but trust me. Here is a square wave. That sounds a bit more like a clarinet or that type of instrument that has a reed. So the reed blocks and releases and blocks and releases and lets air through in that square wave pattern. And so that sounds a bit more like this. Compared to the violin. All right, so all sorts of different basic wave shapes. So these are our basic types of waves. We've got the sine wave, which looks like this, only consists of the fundamental. We've got a square wave, which is the fundamental plus all of its odd harmonics. If 100 hertz was the fundamental, then we'd have 300, 500, 700, and so on. Triangle wave is fundamental and odd harmonics. Sawtooth wave is fundamental and all the harmonics. So they're the basic types of waves, and most signal generators can produce those. But complex waveforms are really where it's at in terms of speech. So it consists, as you saw from that spectrum, of a very complicated looking time domain representation and all of that different frequency content. And as I mentioned, it can have a sort of a repetitive structure when you're doing something like a vowel. So for example, if I go, we had that repeating pattern that we were able to measure. But also when it was aperiodic, when I was making sort of consonant noises like ch, sh, sh, s, all of those sorts of things, there's no repeating pattern there. It is really just noise. So complex waveforms can be periodic in their nature or aperiodic or alternating patterns of both of those. And as I mentioned, we can plot those spectral changes over time in the form of a spectrogram. It's also referred to as JFTA or Joint Time Frequency Analysis. Sorry, JTFA. All right. So just to recap, a spectrogram shows frequency on the y-axis, time on the x-axis, and shows the amplitude either with a color scale, so here you can see warmer colors mean more energy, or it could be white is no energy, black is energy, or vice versa, depending on how you choose to set up your spectrogram software. Okay. Right, there's other things that we can do when we to change the frequency content of sound, and that's called filtering. So filtering is the act of removing sound energy at different frequencies and leaving it behind at other frequencies. So just like a coffee filter lets the water and the coffee flavor through, but traps behind the coffee granules, it's letting some things through and letting other things through. A colander is another example of a filter. It's letting the water through but holding onto the spaghetti. Filtering can remove some frequencies and leave others behind. So if we choose to let the low frequencies pass through and we've removed the high frequencies, we've let the low frequencies pass. We call that a low pass filter. So let me demonstrate that. So here you can see I'll turn down the sound. Here you can see a noise, and it's, as you heard, it's a white noise. It contains all of the frequency content. Just like white light contains all of the frequencies of light, white noise contains all the frequencies of noise. And you can see that here in this spectrum. It's changing over time. But if I average it, let's do some averaging. Are you ready? Look at that. Spectrum is dead flat, so completely flat. How lovely. We'll stop averaging and we'll look at it instantaneously. But you can see it contains a whole range of frequencies across there, all equally present. And that's white noise. But if we low pass filter it, we're cutting out some of the high frequencies and letting the lows pass through. So let me show you what that looks like. I can add a filter here. I'm going to add a low pass filter. And here you can see this is what the high frequencies were shown in gray, and we've filtered them out, and now it follows this pattern of decreasing like this. So this is the result of that filter function. The filter function we've applied is shown in the black line that you can see there. It has a particular cutoff frequency after which things start to die away more rapidly. So here I'm going to set that cutoff frequency to be, let's say, 3 kilohertz. And here's what that sounds like. And then I'm going to shift that filter frequency and you'll hear how that sound changes. All right, so one thing you may not know is that telephones have a restricted frequency content compared to real speech. So whereas our speech is, if it's live, it's unlimited in its frequency content up to the limits of our hearing and voice production. But sound that it goes through a telephone system is filtered. So only sounds between 300 hertz and 3 kilohertz get through. So if I change this white noise and low pass filter it at 3 kilohertz, it will sound a bit like it's been passed through a telephone system. So here it is here. So that's a little bit more like a phone system. The opposite of low pass is high pass. And so this is where I remove low frequencies and let the high frequencies through. So for example, here is that same noise, high pass filtered at 1 kilohertz. It's starts to remove frequency content below 1 kilohertz. And here's what that sounds like. All right, very good. Now, what happens if we apply a high-pass filter and a low-pass filter simultaneously? It's kind of what happens when we pass sound through the telephone system. As I mentioned, it only lets sound in between 300 hertz and 3 kilohertz. That's called a band pass filter because we're letting a band of frequencies pass through. So let's set this one here at, let's be like the phone system, 300 hertz and 3 kilohertz about here. And here's what that sounds like. That's very much like a phone. I can take out even more. So what I've done there is only let through a narrow band of noise centered around 1 kilohertz. And I could do the same at 2 kilohertz. So let's do a narrow band of noise centered around 2 kilohertz. And that sounds like this. Sounds like crickets at night. So that is called narrowband noise. And the opposite of narrowband is when I let through a lot, when I have a very broad band. So this is, again, broadband noise or white noise. So you might be familiar with the word broadband when it comes to internet and the transmission of information. It's talking about like a wide stream of information. So it's the same sort of concept where we're letting a lot of energy through. Okay, so that's a band pass here. Here's a band pass. The opposite of a band pass is a band stop filter. So that's where we instead remove all the energy within a certain range. When I say all, it's actually it's got a slope to that function, and we call that the slope of the filter. So for example, if I go back to a low pass filter, here you can see that this type of filter is called a fourth order filter. Let's switch it to a first order filter. You can see it's diving off quite slowly. The higher the order of the filter, the steeper the energy falls off. Basically, it means how many times are we refiltering it? We filter, 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 and we can get steeper and steeper filter functions. So that's the order of the filter. So just to recap those, here's a low pass filter. We have a certain corner frequency above which we start to remove content. A high pass filter is we let the high frequencies pass, we remove the lows. A low pass filter and a high pass filter together, one after the other, gives us a band pass filter. We're letting only frequencies within a certain band get through. So first step here is we've taken out the highs with the low pass filter, and then the second step is we've taken out some lows with the high pass filter, and that gives us a band pass filter. And the range of frequencies that we let pass, we call the pass band. All right, so we apply filters all of the time. So one example is for adjusting the settings of a hearing aid. That's using filters, a variety of filters to match the frequency output that would best suit the person's particular hearing loss. So you'll find filters being used all the time there. But in the speech domain, really, it's our whole vocal tract which is doing filtering, and that's how we saw those differences in those vowels, was due to the fact that I'm producing a sound from my vocal tract which has got a lot of different frequency components, and my tongue and my lips and where the tongue sits in the vocal cavity, in the mouth cavity, is creating filters and accentuating some frequencies and cutting out other frequencies. And that is the basis of the different vowel sounds that we have access to. All right. So let's talk about the application of frequency and intensity to the act of doing audiometry. So you've seen an audiogram before. It's basically we have frequency on the x-axis and amplitude on the y-axis, but amplitude in this case is in decibels, hearing level, dBHL. And because it's leveled out so that 0 dB is normal hearing for very, very young, like 18-year-old college students in the US when they gathered that data, 0 is flat, and a flat hearing loss means we've applied the same amount of hearing loss, or we've got the same amount of hearing loss at all of the frequencies. So if your hearing loss is less than 20 dB, we call that a normal hearing loss. Anything from below that is mild, followed by moderate, severe, and then profound levels of hearing impairment. But the speech that I mentioned earlier has different frequency components. You saw it on the spectrum, you saw it on the spectrogram. We've got low frequency components and high frequency components. And we can represent that on the audiogram in the form of this structure here called the speech banana. So here you can see the further down the phoneme is, the higher amplitude it is, the more intense it is. And the more to the low frequency end, then that contains more low frequency content. More to the right contains more high frequency content. So over in this range here, we've got vowels like E, U, R. They're intense with low frequencies. And up here, we've got this batch of consonants which have very high frequencies, but much lower energy, much lower intensity. So f, sh, s, f, for example. All right. So speech, as I said, is made up of different components, each with different frequencies and amplitudes. Vowels are low frequency and high amplitude. Consonants are high frequency and low amplitude. So which are harder to hear? Well, really, if you've got a conductive loss that's flat, so a flat line descending across here and limiting your ability to hear anything quieter than that level, then a flat hearing loss is going to affect the high frequency consonants first. So for example, here's an example of someone with perfectly normal hearing, but if you have a conductive overlay in the form of an airborne gap produced by, say, middle ear infection, what you see here is that as the middle ear is filling up with fluid, we've got this descending of those air conduction thresholds. The first things that become inaudible are those high frequency consonants. And so you might find in your role as a speech therapist, for example, that a child who has persistent ear infections and a consistent conductive hearing loss will have difficulty hearing those very quiet components of speech, and they may not use plurals properly, for example, or may have difficulty reproducing those consonant sounds because they have difficulty hearing them in the first place. All right, so usually high frequency consonants are the first that are affected, and most sensory neural hearing losses as well tend to affect the higher frequencies first and more detrimentally. So here's an example of speech spectrograms for a normal hearing listener at the top and someone with a sensory neural hearing loss at the bottom with a sort of a moderate to severe hearing impairment. And you can see the energy contained in the phrase, she sells seashells by the seashore. We've got a lot of that high frequency consonant information going up the page. But when we filter that out as a result of a hearing impairment, you can see that all we're left with is the vowel information. So instead of she sells seashells by the seashore, what we have is E-L-E-L by the E-or. And that might be, that's sort of one characteristic of what is sort of often known as deaf speech. So someone with a profound hearing impairment who just hasn't heard those high frequencies tends not to learn to produce those sounds. And so that's sort of the reason why that sort of speech pattern exists. So what are we trying to do when we are treating a hearing impairment? We're not fixing the hearing. When we provide amplification, we're not making the hearing thresholds better. All we're doing is taking that speech and moving it to the audible range, like so. So we need to boost the different sounds at different frequencies by different amounts. And that's where the filtering comes in the amplification devices. All right, I'm going to take a few moments now to talk about the principles of calibration and the idea that for a device to work properly, like our sound level meter that I mentioned earlier, it needs to be properly calibrated, and that means that it needs to be measured against some other device, whose properties are known. But how do we know the properties of that device? Well, that device had to be calibrated against another standard, and so on, back and back towards the original standard. So it's it's really a widespread thing that we need to consider among all of our devices, whether they are producing sound or measuring sound, or producing electrical signals or measuring electrical signals. So the components of an audiometric testing system that need calibration are the audiometer, and so we need to calibrate the oscillators to make sure that the frequencies they're producing are correct, the amplifiers to make sure that they're making the sounds at the right level to begin with, and then the attenuators, so the dial that makes it quieter or louder. We need to make sure that a 5 dB step is indeed a 5 dB step, for example. In terms of our transducers, we've got headphones, supraaural headphones, we've got insert earphones, bone conductors, and free field speakers. All of those have to be calibrated in different ways. So the headphones get sat on a special coupler with a microphone underneath them. The insert earphones we can use with a test box where we couple it with some blue tack around a little microphone. The speaker, again, we can hold a sound level meter a certain distance from that speaker, measure the output level. The bone conductor, we're not measuring sound output, we're measuring force output. So we need a special force transducer to calibrate our bone conductor. So we don't have one of those. So we periodically ship all of our stuff up to a private company in Auckland that does that. We do that annually, and then they send it back with a tick and a certificate. The other thing when we're talking about calibration that we need to take into account is the calibration of the acoustic properties of a particular space. So that might be ensuring that the room is quiet enough. So this room, to me, is pretty quiet. The only noise is coming from the recording equipment itself and a little bit from the ventilation. And as we saw earlier, that was about 40 dBA. Very, very quiet for a typical quiet office level. But for example, a classroom might be considerably more noisy than that, and we're trying to reduce those levels. The other thing that we need to measure is how reverberant the environment is. Now, when sound impacts on a hard surface, it reflects back, and you might hear that as an echo. So if I clap my hands, it might go depending on if it was very far away or not. But the summation of lots of different echoes together forms, where they become indistinct, forms reverberation. And so that's like, the difference between when you're in a small room and a large cavernous space that will sound more reverberant. I'll play you some examples of that. Okay, so first let's talk about calibrating the sensitivity and the frequency response of a transducer. Now, by transducer, I mean anything which converts from electricity to sound or from sound to electricity, but really that's only in our specific context. Anything which converts one thing to another thing is a transducer, like a force transducer or anything like that. So there's a whole variety of things which are transducers. When we're talking about something like a microphone, like the one that's up here, there's two things that we really want to know about it. Firstly, what is its frequency response? So does it record equally across all of the different frequencies? The second thing we want to know is what's the sensitivity of the device. So if I play a sound at it, what's the size of the voltage I get out of my device? So what's the voltage coming out of this microphone that is informing our measurements? Similarly, the other way, so if I think of something like some insert earphones, here's some insert earphones of mine. The speaker is contained within this box. What I want to know is how good is it at producing sounds at all of those different frequencies as they come out of this tube, and also how loud is the sound overall. When I plug it in and put a certain voltage, what's the decibels that come out the other end? And so we can either state that in numbers or in a graphical format. So for a condenser microphone like the one that's found at the end of this sound level meter, we might see a chart like this. So this is showing you that it's got a very good frequency response. It's relatively flat across a wide range. Let's looking at this number here, this top line. It's very flat across a wide range of frequencies, kicks up and then drops off drastically at around 40 kilohertz, so well within our needs. And over here we've got some numbers here which are showing the sensitivity. So how many microvolts are we getting out per Pascal of signal? So there's our sensitivity, and here's our frequency response. So these particular headphones that you see right here, these exact headphones are calibrated specifically, and they have, if we look on the bottom on the screen here, you can see they've got individual serial numbers, so that this one was calibrated and this one was calibrated. If we look at the calibration for the red one, I'm showing you on the screen here, that was calibrated on the 11th of September, I think probably 2014. And you can see that it met their characteristics, and you can see it's got a very, very flat frequency response up to a certain level. So that means that these are really great headphones in terms of the flatness of their frequency response. The other thing is that we can see what the output is for a certain voltage drive. So for example, when I put 1 volt RMS, there's that name again, if I put 1 volt RMS into this, I get 99.5 decibels out when I'm measuring at 1 kilohertz. So that's our sensitivity, and then we've got our frequency response there. So those two things are good to specify the characteristics of that particular transducer. All right. So how much variance do we tolerate? Really, it depends on what it is that we're measuring. So for example, in an audiometer, the frequency that we specify has to be correct within 3%. So if I think I'm putting out a 1 kilohertz tone, the machine has to be doing something between 970 and 1030 hertz. Somewhere in that range is fine, because that's near enough. Anything outside of that, we start to be sort of getting away from the essential 1 kilohertz nature of our stimulus. In terms of amplitude, the overall absolute amplitude has to be correct within plus or minus 3 dB if we're dealing with sounds up to 4 kilohertz. And at frequencies above 4 kilohertz or below 500 hertz, then it has to be correct within plus or minus 5 dB. So that means when you see a number on an audiogram that says the person's hearing threshold was 30, plus or minus means it could be anywhere between 25 and 35. So we have that sort of leeway depending on what frequency we're looking at. That is just not anything to do with the person and how they're behaving, but the tolerance that we accept in the equipment itself. When we adjust the dial on the audiometer and go up by 5 dB, it has to be 5 dB within 1 dB or 30% of the interval step, whichever of those two things is smaller. So for example, if I say it's a 5 dB step, it's either got to be between 4 or 6 dB, so somewhere in that range, but nothing outside of that range. In terms of the distortion of the equipment, we can only tolerate a maximum of 3% distortion for headphones and 5% total harmonic distortion for bone conductors. Now, we didn't speak about this, but I'll give you a quick demonstration of what that sounds like, a pure tone versus a tone with a certain amount of total harmonic distortion. So remember, those two numbers are 3% for headphones and 5% for bone conductors. Okay, so here is a 300 hertz tone that is pure. It's a pure tone. You can hear it sounds lovely. It's undistorted. What I'm going to do is add some distortion now, and it's going to be symmetric clipping of that signal. So as I move these dotted lines down, I'm going to be chopping. I'll just turn down the sound for a moment. As I move those dotted lines down, I'm going to be chopping out more and more of the tips of that waveform, and that's going to introduce high frequency splatter and high frequency harmonic content. And watch what happens to the sound and also to the measurement of total harmonic distortion that we see here. So I'll increase it and I'll stop at 3%, which is what we can tolerate for audiometric headphones. Okay, so we've gone from being a pure sine wave to having all of these different harmonic content and a sound that sounds more like this. Compared to that pure tone. So that is the degree to which we tolerate distortion. The reason distortion is important is because let's say you can't hear that 300 hertz tone, but you can hear higher harmonics. You might push the button in response to one of these harmonics instead of to the original fundamental. Okay, what's also important is how quickly we turn on and off a sound signal. So when you push a button on an audiometer to present a sound, it doesn't immediately turn on. It slowly ramps on over about 20 to 50 milliseconds and then slowly ramps off. So it goes instead of like that. So that means that we are restricting the amount of sound energy to just the frequencies we're interested in. Okay, so we can have acoustic noise in the environment. We can also have electrical noise from things around us. And in order to have a booth that's properly functioning for hearing testing, we need to be able to specify the minimum level of acoustic noise which is present in the environment. And so we can do that not using a sound level meter like this. This will tell us the overall level, but we are really interested in the sound level at specific frequencies. And so for that, we use a proper sort of spectral analysis. So we've got certain standards that we need to use. So for example, this is a brand of booths, and you can see this is the type of attenuation or noise reduction that they provide or accept. So in this case, this purple one here, you can see that it is blocking out so much more sound than these other ones. And the reason for that is this is for a double-walled booth. So this is where you have a soundproof booth and you enclose that soundproof booth in another soundproof booth. We've got one of those downstairs, and I'll show you some video of that in a moment at the end of this lecture. So you can see that we can take all sorts of measures to reduce the amount of sound that enters our particular environment. Okay, so let's now talk about how the sound affects things in the real world. What I want to quickly talk about is the way sound moves through space and propagates through a space. So we talk about the environment in which sound moves as the sound field. So you might hear the term sound field audiometry. That's where you've got a speaker in a room and the child or whoever you're testing is also in that room. So that's the sound field. You're testing them in the sound field. And that just means it's a space with sound in it. There's a more idealized situation which we call the free field, and that assumes that there are no barriers around and that the speaker is like in the middle of the sky or something like that, with absolutely nothing around it but pure air and no reflections or anything like that. That's a free field. So when we're talking about this idealized spread of sound, that's free field conditions means that there's no reflections or anything like that. So obviously we can't suspend speakers and microphones at 30,000 feet or whatever, because it's noisy and there's a variety of things going on there with wind and stuff like that. So what we have to do is replicate that as best we can with an anechoic chamber. So an anechoic chamber is something where all of the surfaces are treated to absorb sound reflections, and that reduces that reverberation time, reduces all of those echoes. All right, so the other thing about a free field is we're assuming that sound is moving spherically perfectly in all directions and that the sound is emanating from a single point in space, like right here. Whereas in reality, so for example, my voice isn't a point source. It's going to be louder in front than it is from behind because the rest of my head's in the way, for example. So it's not an idealized source in that sense. And what happens when sound is emanated from, let's say, from the tip of this tuning fork, is that sound travels out in all directions. Now, you know from experience that when you put your ear very close to that sound source, it's louder, and when you're further away, it's quieter. But you might not have considered the reason why that is. It's to do with the fact that when we talk about that sound propagating out in a spherical way, it's really that sound energy that is emanating from the source. As the sphere gets larger and larger and larger, that sound energy is distributed across the surface of that entire sphere. And because, this is some more maths for you, because the formula for the surface area of a sphere is 4 pi r squared. Do you remember that? 4 pi r squared. So it's just some number, 4 pi, times the radius, or your distance from the source, squared. So why is that important? It's important because if let's say I'm at a radius of this far, then I've got a certain amount of energy. If I double the radius, so instead of being instead of being 30 centimeters away, if I'm 60 centimeters away, then the energy that was spread over this one area here is now spread over 4 times that area. Do you get that? So here, if we've got an area of 1 and I double the distance, doubling is a factor of 2. 2 squared is 4. So it's now the same area would only have a quarter of the energy. If I went 3 times that distance, so 30, 60, 90, instead of the amount of energy that I had in this area here, if I'm going out this far, I've now got a 1/9 of that area, because 1, 2, 3 squared is 9. So it's a rapid reduction in that sound level. Here's a sort of an analogy. So if I get a balloon like this and blow it up a bit, like so, and let's say with a marker I draw on it and colour it in. Can you see how that's lovely and black there? That's the amount of sound energy which is impinging on this little part of my, my sphere. What I'm going to do now is increase the diameter of this sphere by blowing up the balloon a bit more, and see what happens to the blackness of this black. Can you see now that that energy has been dissipated, not in a very uniform fashion, but can you see how now it's spread out and less black than it was? Okay, and now we're going to let out some air and undo that. And look how much blacker that is. We've reduced the area over which that energy or the ink has been spread. I'll throw that down there so it doesn't get black on everything. Okay, so that property of the intensity changing with the square of your distance from the source is called the inverse square law. Inverse because it's getting smaller, not larger. So if it was getting larger, that'd be the square law, but it's not. It's the inverse square law. So that's the intensity, the amount of energy. But energy and sound pressure are not exactly the same. So sound pressure, instead of being proportional to the square of distance like intensity is, sound pressure is just proportional to the distance. So if I double the distance, I halve the amplitude of the wave, the sound pressure. And do you remember from our decibel chat earlier what a halving of amplitude is? It's a 6 dB reduction. So what that means is if I'm here at 30 centimeters and I measure a sound level of, let's just pick a number and say 60, then if I double that distance to 60 centimeters, what was 60 here is now 6 dB less when I'm here, so it becomes 54. This 60 centimeters, if I turned it into 120 centimeters, I would lose another 6 dB. So I'd go from 54 down to 48, and so on. The and so on bit is quite important because you'll note that to drop by 6 dB, I only had to move another 30 centimeters. But to drop the next 6 dB, I had to move by 60 centimeters. And then another 6 dB would be 120 centimeters. Another 6 dB would be 240. So the sound dies off really rapidly when you're very close, and then at a slower rate the further and further you get from it. In fact, that's one of the cues that we use to judge the distance of a sound, is that as I move closer to it, how quickly does the sound level increase? All right. So in the real world, there are lots of obstacles. It's not, we don't live in a free field. We live in sound fields which have objects and things which have different absorptive properties for sound, different reflective properties. And sound travels into and out of walls and structures in different ways. And we call that transmission of sound through those structures. So all of those things have to be taken into account. So when there's an obstacle in a sound field, the sound can interact with that obstacle in a number of different ways. So firstly, the important thing to note is that it depends on the wavelength of the sound. So if I've got an object like this water bottle or the one on the screen, and sound is moving past it, if it's a low frequency sound, those sound waves will just wrap around it and keep on going like it was never there. And that's because this object is very small in comparison to the wavelength of the sound. On the other hand, if I've got a very high frequency sound, its wavelength is very small compared to this object, and so that's going to be blocked by an object of that size. So the key thing to remember is that low frequencies wrap around objects and aren't blocked as much. High frequencies are blocked quite easily. So here's an example. Here's a low frequency, and here is a high frequency being blocked by, for example, your head. That's actually a really important cue for when we are judging where a sound is coming from in space. So a sound from over here, a high frequency sound, will be more intense in the closer ear and lower in the further ear because of the head shadow effect. My head is blocking that sound, and this one is picking up a lower level of the sound. On the other hand, what do we do for low frequencies, which are just going to wrap around my head? In those cases, we can't use the level differences, what are called interaural, between the ear, interaural level differences. Instead, we use interaural timing differences, because our neural circuits can measure the time it takes, or the phase difference between the sound hitting this ear and then hitting that ear. And so we use a combination of those two things, ILDs, interaural level differences for high frequencies, interaural timing differences, or ITDs, for the low frequencies. We'll talk more about that a bit later. But that's the head shadow effect. That's the other reason also, those of you who have got home theatre systems that consist of tweeters and woofers, and subwoofers, for example. So we have speakers which give us high frequency information, and typically when you're setting it up, you'll put one on one side of the screen, one on the other side of the screen, so that you get some sense of left and right when you're listening to the stereo image. But the subwoofer, literally you can put it anywhere in the room, it doesn't matter, because it just is the room. It doesn't have a direction, it's just there. You can't judge that direction. The sound is just going to wrap around all of the objects. So you can put the subwoofer anywhere, but you put the high frequency speakers in specific left and right locations. All right, so within a room, sound may follow multiple paths to reach the listener. So for example, this microphone is picking up the sound right now, and the direct path is literally from my mouth to the microphone. That's the first sound that it detects. But there's also reflections of these hard walls. I've got two hard walls. I've got an acoustic ceiling above me. I've got carpet on the floor, carpet behind me, and big curtains on that side and big curtains on that side. So these big heavy curtains are reducing the amount of sound that's bouncing around, because when sound hits it, it gets absorbed. But these hard surfaces that are here and here reflect sound off. And we can adjust the acoustic properties of this room just by changing the space that's taken up by curtains versus the space that's taken up by hard surfaces. So sound energy bounces off things just like when you throw a billiard ball around a pool table and it moves around and bounces off the cushions. Just like that, you can do it in 3 dimensions, and that gives you an idea of where sound travels in a space to reach the ear of the listener. And so it's going to be different depending on where you are relative to the listener. So if you're very close, the sound level that is the direct signal is going to be very loud in your ears. And if you're right at the back of the room, because you're getting further and further, the inverse square law means that sound level is going to drop off, and you'll have less of the direct sound. But the proportion of the sound which has already bounced off some other object before it hits your ear will be greater. So you'll have more of that diffuse field or reverberant field sound reaching your ear. Okay, so reflections are really an important factor of defining the properties of an acoustic space. So if I clap my hands, what you would see is the first reflections, the second reflections, and so on, and they would decrease in amplitude in a certain way. So if I go, there was basically not much of an echo that you could detect there. But in other environments, I'll clap my hands in the stairwell just over there in a moment, and what you will hear is when there's lots of like purely hard surfaces, not a single soft surface inside, it's a vast difference in the sound and the amount of reverberation that occurs. So let me just give you a quick demo of clapping my hands just in front of the stairwell where there's a lot of carpet around. Then I'll step inside the stairwell, clap it again where it's all hard surfaces, and you'll hear the difference in those two claps. All right, so that was pretty remarkable difference between those two things. So when you're designing a space that's meant for lectures, what you want is to have the sound level grow and reach the listener's ears at a very high level, and also you want the sound to die away at a rate that you can control by defining the properties of what you build the room out of. So you would have different requirements for a room that is designed for talking versus a room that's designed for listening to music, for example. So an example of that is a recording studio. They will take great effort to deaden all the reflections and make sure that any sort of acoustic properties are ones that they have total control over. So they can make it more echoic and reverberant by adding a bit of echo. You can do that electronically as well as like acoustically and physically. But yeah, so you have different needs for different environments and different purposes. All right, so how much reverberation is desirable? Well, as I said, it depends on the use of the room that you intend. So here's a chart that you can look at, which is saying that, for general purposes, if I've got an auditorium and I want a bit of speech and music, then that's 1.5 to 2.5 seconds. Reverberation time is probably the limit. But if I want clear articulation, like a classroom, I want kids to be able to hear stuff, I shorten the reverberation time down to, say, 1 second or hopefully a lot less than that. Anything greater than 2.5 seconds, it's going to impact on people with hearing impairments first. So anyone with auditory processing disorders or sensorineural hearing impairments are going to have a lot greater difficulty in a reverberant environment than someone who's got good auditory processing. The reason that reverberation has a big impact on speech intelligibility is because of the low frequency sounds have a lot of energy and they tend to swamp the high frequency sounds, which give the crispness and definition of the words and contain all the consonant, high frequency consonant information, which is really important for intelligibility. So let me show you some examples of that. Here are some recordings that have been processed to simulate reverberation in a recording studio with no reverberation at all versus Grundtvig's church in Denmark, which has a very long decay time. So firstly, I want you to tell me what the speaker is saying in this recording.
In doing so, he became the founder of modern acoustical engineering. He went on to design acoustics of Boston Symphony Orchestra,
Okay, so that's still going, that reverberation. I think you would have had a lot of difficulty in understanding what he was saying despite the Danish accent. Here it is with a shorter reverberation time. So that's either a smaller acoustic space or you're closer to the speaker.
In doing so, he became the founder of modern acoustical engineering. He went on to design the acoustics of Boston Symphony Hall, still considered one of the best halls in music in the world.
All right, so that's an improvement, clearly, but here's the original with no reverberation whatsoever.
In doing so, he became the founder of modern acoustical engineering. He went on to design the acoustics of Boston Symphony Hall, still considered one of the best halls for music in the world.
Right, so it's clear there that the dry environment with minimal reverb was best for acoustics of speech. But what about for singing? How would that be different? So here's an example of singing in that same church simulation. All right, I'll quit that. Here it is with a shorter reverberation time. So that's nice in that you get that ringing, and you can actually hear the difference between fast bits and slow bits, which is quite good. So that's a property of, you might be familiar with like Gregorian chants or sort of medieval music. It was all designed to be performed in these ridiculously reverberant spaces, and so they have very slow moving bits and not lots of fast choppy bits. If you tried to play rock music in that sort of environment, it would sound awful. But that was clearly beneficial for the sound of that voice, because here's the singing, but in an acoustically dry environment.
Ba-ba-da-dee-da-ba-da-dee, ba-ba.
There we go. All right. And here's what a pure tone sounds like in that space. You can hear that dying away exponentially. All right. So what about classrooms? I mean, that's a really key consideration when we're dealing with children and their ability to hear and learn via spoken language is their ability to hear in a classroom situation. So I really like this quote from Lubman, which is we put children in classrooms where they can't hear, but we'd never put a kid in a classroom with the lights turned off. So the point there is, you know, they need access to information that is coming via all the different senses, and to build an acoustic space that just doesn't perform for its task is a bad idea. So you may, I assume you'll probably be aware of the move to modern learning environments or flexible learning environments that has occurred in recent years with all new school classrooms that are built are basically open plan to some extent. They've got sort of dividers between areas, but children and staff are free to move between the spaces, but also sound is also free to travel amongst those spaces. So that has been quite a concern for anyone who knows anything about children's ability to learn. And these spaces might be okay for kids with good auditory processing ability and good hearing, but any child with an impairment in either of those skills are going to be suffering disproportionately when they're in a space that doesn't behave acoustically. So to ensure that the acoustic properties were as good as they could be, the Ministry of Education released these guidelines that you can see here, which covers things like reverberation time, what's an acceptable amount of reverberation time, the amount of sound insulation between adjacent learning spaces, what's the impact sound insulation. So we've got sound coming from a road outside, how much of it gets in the building to begin with, and what ambient background noise levels are we able to specify. So for example, it also walks through a number of scenarios and gives detailed descriptions on how you might improve the acoustics of a space if you've got a particular problem. So if your problem was there's lots of background noise level coming in from outside, then you can improve the performance of the outside of the building, the facade, or you can put some shields up in the form of earth banks or walls or things like that will block the incoming sound. Bushes don't tend to do quite so much. If you've got high background noise levels from sources that are inside, then I like this one, remove, replace, or mitigate the sound source. So if it's little Johnny that's making all that noise, you kick him out of the, no. If it's, so for example, an overhead projector, or sorry, like a data projector has got a very loud fan, mitigate that source by getting one with a quieter fan, for example. Same with the ventilation systems in the room. Again, you can improve the way you seal off the gaps between spaces. If there's too much reverberation time, then you can improve the acoustic characteristics using curtains and things like that. If a teacher is finding it difficult to project their voice, then sound field amplification is something which is really useful for people with hearing impairments. But you don't want to just add to this wall of noise. So if all of the teachers had their voices amplified, that might just have the effect of raising the background noise levels in a sort of an uncontrolled manner. Whereas if you have things which are like FM systems or Bluetooth enabled devices which can put the teacher's voice in the kid's ear directly, that might be a more appropriate means of keeping the overall noise levels down. All right, so when we talk about the ability of sound to get into a space, we often use the term transmission loss, and that's the difference in sound level on one side of a barrier to the other side of a barrier. So for example, if it's 80 dB outside and 35 dB inside, that's a transmission loss of 35 dB for that wall. Again, there's that property of if I double the mass or the width of that wall, that's going to reduce or increase the transmission loss by another 6 decibels. So if my wall is that thick and I get a 45 dB transmission loss, if I want a 51 dB transmission loss, the wall has to now be that thick. So obviously that's impractical. No one's going to be building walls that are that thick just for another 6 dB of transmission loss. So we need to do other tricks, and that includes having mismatches between what we call the impedance of different layers in the wall. So if you have a wall which is high impedance, like so, air, which is low impedance, and then another wall, which is high impedance. The sound has difficulty moving from one high impedance medium to low to high again. And so we get internal reflections and losses in there. So the reverberation guidelines for different spaces that are sort of acceptable, you can see here on this chart from the Ministry of Ed. But things like, I spoke about the differences between soft fabrics like this and hard walls or glass, and that stairwell example, that was 100% reflective. So that was made of concrete. Basically, every single surface was concrete. And so the amount of sound that is reflected off concrete is close to 100%. Very little of that sound energy is absorbed. Whereas as soon as you get a surface that has some soft covering, that is going to absorb the sound a lot better and prevent those subsequent reflections. So that property of a material, the amount of sound it absorbs at different frequencies, is called its coefficient of sound absorption. And it was developed, that principle was developed by this guy, Wallace Sabine. And so we measure the units, just like we use hertz for frequency and pascals and newtons. The unit for sound absorption is sabins. I don't think that's an SI unit, but it's one that's commonly used. It's definitely not SI because it's talking about 1 square foot of a material, and we don't talk about square feet. All right, so absorption coefficient of 1 means the sound is 100% absorbed, and the only way you can achieve that typically in practice is to open a window. So if sound heads out the window, it never returns. That's perfect sound absorption. But everything else is going to have a sound absorption coefficient of slightly less than 1. And an absorption coefficient of 0 is total reflection. So if 55% of the energy that hits the wall, if 55% of that energy is absorbed, then we say that material has an absorption coefficient of 0.55, and 1 square foot of that material has an absorption of 55 sabins of absorption. You don't need to know that. And we measure those absorption coefficients at lots of different frequencies. So the fact that we have to measure it at lots of different frequencies means that, say, for example, low frequencies might be absorbed and high frequencies reflected, or vice versa, depending on the properties of the room. And so what that means is the rooms act as filters, and the particular acoustic properties of a space are unique to that space or that combination of materials. And by altering the combination of materials, you can boost some frequencies and cut others. Okay, so here's a chart from a sort of an architectural resource book, which says these different materials, we've measured the sound properties, the absorption coefficients at these different frequencies, and here's how we can describe them. So one thing I particularly like here is they've measured the absorption characteristics of an audience member. How much does a typical audience member absorb? What's really cool about that is, let's say you design a massive concert hall and you make sure all of the walls have exactly the acoustic properties that you want, and you've got all of the chairs and they've got the acoustic properties that you want. What you don't want is for the sound in the theatre to be different if there's people in it versus if it's empty. So if it's half empty, the sound will be totally different, for example. So what you do there is you measure the sound absorption spectrum, or the sound absorption coefficients at different frequencies for a typical audience member, and you make sure that an empty seat has exactly the same absorption properties. And that means there's no difference between, other than the noise that the people make, between an empty concert hall and one that's full of people, which is really cool. But let's have a look a bit closer at these. You can see that the concrete of our stairwell that we demoed in has very, very low sound absorption coefficients. That means a very high level of reflection at these different frequencies. Whereas things like curtains, depending on the weight of the curtains, they might absorb 60% of the high frequency sound energy, much less at very low frequencies. So curtains will reduce those high frequencies more than the low frequencies. All right, here's some examples of those. So one example is acoustic foam. The cool thing about acoustic foam, you can see how it's made up of all of these different triangles. The way that works is, let's say I've got all of these triangles that are like this, like so, and sound comes in. Sound when it, whoops, that one is going to miss. Never mind. Sound coming in when it hits an object. The angle of incidence equals the angle of reflection, and so it's going to bounce like this. and then it'll bounce off here, and bounce off here, and here, and here, and here, and here, and here, and here. And every time it hits, we get absorption, 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 absorption. And so this gets weaker, 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 weaker. And if we're, let's say we're reducing half the energy, then it's a half, a quarter, an eighth, a 16th, a 32nd, a 64th. And, you know, pretty soon we're down to less than 1% of the original energy just by having multiple collisions. So a triangular structure like that is designed to give you as many of those sorts of collisions as possible. Here's an example from a movie theater. You can see we've got very plush furnishings and lots of draping here, which is going to, you know, absorb reflections and make sure we have crisp, clear sound for the movie we're trying to listen to. The room that I'm in right now, I will show you a quick, I'll just record it. The room we're in right now has an acoustic ceiling. So you can see here it's made up of lots of little holes. And on the screen you can see all of these different little holes. That's a similar use of absorption. So we have tiny little holes that when sound hits in there, it has to reflect around several times before it escapes. And the version that does escape is greatly reduced in energy. So just having the ceiling in here has a good effect on the properties of the acoustic space. You might be familiar with the trend for cafes and things like that to go for hard concrete everywhere. It's very easy to clean and all that sort of stuff. But it can be very terrible for conversations because it's all these acoustically hard spaces. So what you might see in a lot of cafes, or the well-designed ones, is big absorption panels which are glued to either the walls or the ceilings, which provide a way to intercept that sound that would otherwise reflect off the hard ceiling. So just having a few of those in key locations around makes all the difference to your ability to hold a conversation in these spaces. And I think there are apps that you can use to rate the acoustics of different environments. So if you've got a hearing impairment, you'll say, well, no, we won't go to that cafe. Let's go to this one, which has better acoustics. All right, here's an extreme example where those triangles that I mentioned earlier are covering every single surface in that space. So this is an anechoic chamber that I visited in Copenhagen at the Technical University of Denmark. And what you're seeing that looks like a floor here is actually a wire mesh. And so below that is a whole other, just a continuation of those absorptive surfaces. And so that's called an anechoic chamber, meaning no echoes. And it's really a cool environment. You clap your hands and that's it. The sound, once it hits the walls, that's the last you hear of it. There's no echoing whatsoever. Here's a cool example of a video, of a balloon being popped in an anechoic chamber versus in a really reverberant environment. Sorry, first is the reverberant environment, then the anechoic chamber.
Wow.
All right, so our lecture theatres around the university have these properties taken into account in their design. So here's an example of a typical UC lecture theatre. This is from a few years ago. It's been renovated since, as you can tell by the colours. But what you see here are different panels here which reflect sound to keep the speaker's voice at a high level. So we don't want to, if your goal is to let people hear the sound, you don't want to be, absorbing it completely. You want to have some reflections in there. But the other thing that you can see are these wooden panels here. And one day I was in there and saw that looking up through here at these panels, that behind them is this sort of acoustic foam. So the sound goes through the little holes and is absorbed by the foam. So that sort of foam, like a spongy sort of material, the sound bounces around and has so many collisions that all the material is just dispersed, all the sound is just dispersed as heat energy. All right, so I'm going to finish up now talking very briefly about soundproof rooms or soundproof booths and why they are important and how we can use them. So basically, when we're doing audiometric testing, it's very important to have a controlled acoustic environment so that the person's hearing thresholds aren't made worse by excessive levels of background noise, for example. So one way that we can do that is by enclosing them in some sort of box or cabinet type thing, or a telephone booth style structure, which prevents the inflow of sound from the outside world. And there's a whole heap of things that we need to take into account. So firstly, if you're buying a soundproof room, you're not buying the end result. You're not buying the noise floor. You're buying the transmission loss and the amount of attenuation the booth provides. So if I'm producing an acoustic booth for you and you decide to put it on the median strip of a freeway, and there's lots of trucks and things running by, that's your problem, not mine. Really, all it's going to do is reduce it by a certain amount. So you've got to combine your placement of that booth with with its acoustic properties to give you the end result in terms of the noise floor. So there's the two things that soundproof rooms do, and I'll show you some examples in a video in a moment. One is that it has to reduce the sound entering from the outside. The second thing is that any sound that does end up on the inside needs to be absorbed as quickly as possible to prevent the sound from reverberating around too much. Sound, a few more things. Sound can travel through the air, like the sound that you're hearing now, but it can also travel up through structures and through walls, and can be borne by structural borne vibrations. So again, if you've got some very heavy air conditioning equipment that is bolted to the building, and your booth is bolted to the building, you could get a hum, a low frequency sound rumbling up into your room, which would disrupt things. There are a whole heap of methods that we can use to isolate the structure from its surroundings. So I said if it was bolted to the floor, you wouldn't do that. What you would do is sit it on some sort of cushioning layer like a rubber material. And I'll show you some examples from our own booths when they were constructed. And then secondly, lastly, how do you calibrate the soundproof room? Well, essentially, you just make a very loud noise on the outside and do measurements on the inside. And you measure the difference in the sound level from the outside to the inside at all of these different frequencies. And that gives you the characteristics, the absorption characteristics of your room. Things to look out for in a soundproof booth is, as I'll show you in this, I'll go for a little walk and show you as part of a demo. The doors are a weak spot. The windows, the ventilation systems, because you have to have airflow in there, they're a problem. And also the plug boards. So we have, between one space and another, we have little spaces where we can plug and unplug our equipment, and sound can travel through them if they're not properly constructed. One thing I'll just show you with regard to the doors of a soundproof booth is they tend to have a unique structure. And that is, so whereas a typical door, you've got a wall like this and a wall like this, and here is a hinge, and the door fits in the hinge like so. This straight line here and this straight line here means that sound can travel into those spaces. So the technique that's used is you actually have a sloping entrances like so, and then the door is wedge shaped, and these spaces here have acoustic properties. So they've got lots of holes and absorptive filling. So sound which enters here goes bounce, 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 and doesn't make it through, or bounce, 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 bounce. And to make triply, doubly sure, you have big rubber seals here and here and here and here, which extend all the way around the door frame, and that helps prevent the ingress of noise into that environment. Okay, so when I mentioned ways of isolating the structure from its environment, you can use springs such as the ones here, but our booths actually used a rubber kind of arrangement, and I'll show you that in a moment. So I acquired some booths from the UK about 10 years ago for free, actually. These are massive soundproof booths. They gave it to us for free. We just had to ship them from Leeds to Christchurch. And this is the space that we built it in. It's on what's currently called the West Building. And so it arrived flat packed like this. So you can see it's modular in nature. It's made up of all these different panels. If we have a look at the spaces within those panels, they were all filled with rock wool, which is a sound insulation material. Again, lots of little collisions in the fiberglass absorbs sound really well. So just as you've got thermal insulation, you can have acoustic insulation as well. And often they're very similar. So the first thing to do was to lay out very heavy metal base, and then sitting between one metal base and the next metal base was this highlighted zone here, which consists of rubber pads that the room is built on. So there's not a hard connection between the room itself and the floor. They're separated by these rubber barriers that you see there. The air gap that was left between the floor and the floor of the booth, so the floor of the room and the floor of the booth, was filled with rock wool. And then we lay these heavy metal plates on top of it, which forms the floor of the room. Then when you put up the walls, this is a double-walled booth. So you can see here we've got one room that is being built, and that is being built inside another room. So it's a booth within a booth. It's doubly quiet, if you like. And again, all of those air cavities are filled with that rock wool noise insulation. So we've got one double-walled booth there, and next to it is a single-walled booth. You've got to hook up all the electrics. One of the important things about soundproof booths for testing is it needs its own fire alarm on the inside, because when the building's fire alarm goes off and you're in a soundproof booth, you can't hear it. So these are electricians that are wiring up the booth to have that. You can also have distress alarms from the inside to the outside to let people know if something's going on in there. And there we go. So this is pictures of it where it was set up in the top of the West building. We no longer, I mean, this was 2009. No sooner had we developed this facility, got a great amount of use in its first 12 months, and then we had a series of earthquakes. And because it was on the 8th floor of the building, it meant that we couldn't get people up and down it in the event of a power failure, for example. And the people we were testing were elderly people who had had strokes and had mobility issues. And so we had to deconstruct the booths again and move them. And we've moved them to their current location on the ground floor of the psychology sort of building there. So let me show you how they look now. Okay, so this is what those booths look now in their new location, which is looks pretty flash. You can see that the outside of the booth, we've got soundproof, we've got typical acoustic ceilings, we've got carpeted areas. Any windows to the outside are double glazed. So just to demonstrate that, you can see we've got a pane of glass, a big air gap that has a sound absorbing material in there, and then another pane of glass. So the sound from the outside has a bit more difficulty getting through. And then we have our two soundproof booths that you can see here. So this one over here is a single walled booth, and this one here is a double walled booth. I'll turn the lights on and show you. Right, so the single walled booth has this single door that you can see like this, and as I mentioned before, it's got a lot of foam and it sort of fits in like a wedge shape. Even the window within the door has an air gap and is double glazed. And then when we move inside the space, we have carpet on the floor, and then this surface is made up of lots of little perforations, and behind the perforations we have the rock wool sound insulation. And this one here is the double-walled booth. So you can see here we've got one external door, and then there's a gap. This is the wall between the two booths. You can see there's an air gap between those two. And then inside this room is another room, which has its own door. So to get extra quiet, we can shut this one and this one. And here we are. Really, really very silent. There is ventilation that comes through here, which passes through these large boxes that you can see on the outside. And here is the sort of the plug board arrangement that I was talking to you about. So these are typically the weak points of a booth, is the plug boards, the windows, the doors, and the ventilation system. We've also got a range of other booths upstairs. Here's another single-walled booth, this time in blue. And here's a proper sound-treated room, which is designed for testing pediatric clients or children. They sit down in these places. Sound is produced from all different directions, but you can see that we've got acoustic paneling, acoustic ceilings. These doors are acoustic doors. They're very, very heavy and they seal perfectly around their surroundings. And once again, we have that double glazing with the absorptive material in between to prevent sound entering from the outside. And then others are really quite small and portable. So this one is, a really small version. It's got the sound absorptive foam on the inside. Again, it's got windows, but it's designed to be pulled apart and transported. So it can be disassembled, moved to a location, and yeah, it's fantastic. And this is another nice small telephone booth style enclosure. You can see it's got nice perforated walls, all of our equipment through pegboards, a double glazed window, and nice thick rubber seals on the door frame. All right, thanks very much. I hope you enjoyed the tour.